semantics, evaluation, generator expression, function binding later.
I guess the last stream reached 12 hours.
Capital R.
I asked Chatbot to make a branchless solution to getting the highest bit set number without any branches or lookup tables or multiplication.
E O R capital F U N C T.
And I don't know if anybody else uses this technique, but I don't know. This isn't like unrolled. This will probably be slower. I'm gonna set up the mask version of it because Chatbot gave this as an output. I don't know if anybody uses this or not, this technique. I haven't seen it on the internet, so I claim it if nobody has yet. I'm gonna tag this video with some of the description so you can find it later. So if anybody wants to claim this after I'm claiming it, I already claimed this 5-6 videos ago, but I'm claiming it. So anyways.
Undefined. Repeat. Note the bind.
I asked Chatbot to find the highest bit set under those conditions.
Identifier in a generator expression cannot be right.
And Chatbot said,
Object.
alright, so here's what I asked it first.
I've looked on B. Iterate.
And if Chatbot was intelligent, it would be able to connect the dots and give a actual solution to this and remove the branches. But Chatbot is not intelligent, so Chatbot can't make the connection apparently because it got close, but it just can't quite figure it out. Because Chatbot can pass the SAT, Chatbot can do amazing things, but Chatbot is unable to think other than produce training data that has been input. Other than that, there's no thinking involved.
What is the fastest clever technique to get the highest bit set in a STD scissor type? From byte to long to int 128 any size. That does not use a loop or intrinsic. Only masking and bit manipulation to form the value that is the position of the highest bit set.
And then Chatbot said this.
You're asking for a loopless, non-intrinsic, pure bit manipulation technique to find the position of the highest bit set to k and log base 2 floor in an integer, ideally for types from int 80 up to int 128t. This is a classic problem in bit hacks. Let's walk through the cleverest known method that meets all your constraints.
Alright, so Chatbot first isolates the top bit by using bit smearing, the classic technique. I think bit smearing could be merged in with this logic, but I'm not going to figure it out right now. I just figured out how to get, after the bit's been smeared, how to get that bit's position without any math or whatever. And this is extremely long. This could be broken down to simple mask, and then subtract, and then shift. I just want to try this, because the CPU should be able to eat through it because of how it's ordered, and it could potentially be faster, but maybe not. So I don't know, that's what I'm going to test. So I'm going to test this against using a mask. It's the same technique, whatever. So Chatbot isolates the highest bit, and then Chatbot does a D whatever sequence using multiplication and then a lookup table. So I guess that's best chatbot can do. So then, as chatbot,
in a way that does not use addition or subtraction or mult or div.
and then chatbot's like, oh, we gotta use branches.
Now that's a stricter constraint. Restricted symbol, no loops, intrinsics, multiplication, division, addition, or subtraction. Only bitwise operations and masking you want to get the position, int x, of the highest bit set, most significant bit, in an integer using bit hacks only.
It's a number. If you know how numbers work and how columns work, then anybody should be able to simply come to the solution.
Tick. Solution. Bitwise binary search. Using shifts and masks you can simulate a binary search on bit width using only bitwise shifts and masks. No arithmetic required. This approach is pure logic. And it works in constant time with no arithmetic. Let's do it for 64-bit integers first. Can be adapted to 32 or 128.
I don't think chatbot knows what constant time means, because a branch is constant time in worst case, but you wouldn't use constant time in this context. It's just branching involved. This is chatbot's result with pure branching. And it makes a really lengthy result after this, which is why I kinda made this lengthy, whatever. Instead of this, I can mask to remove all the shifts and stuff and account for it with a single subtraction to get the sign bit and then shift that bit. It's like only a couple operations. This is just the long way to try it. But from this, chatbot, if it was intelligent, if it can pass the SAT, if chatbot is what everyone says chatbot is, chatbot should be able to see the connection between a branch and an assignment and remove it. It's like clearly right there, chatbot has all the info, but chatbot can't connect the dots because no one trained chatbot, because no one taught chatbot, because chatbot does not have, it's not intellectual. It needs somebody with intelligence to program chatbot for training data. And the people that made chatbot, they must not be the most intelligent. I don't know. What do I know? And then the edge case. Okay, whatever. So chatbot's like, look, I met all your conditions. And it's like congratulating itself also.
Perfect. Now we're at full hardcore bit hack mode. You want to brain compute the position of the highest set bit without loops, intrinsics, addition, subtraction, multiplication, division, lookup tables, branches, that is no if, etc. Only bitwise logic and shifts.
Okay, that was after I asked it a question. I asked it without branches and stuff, whatever. And then it said that. And this is the solution. This is actually very close to how to do it. Okay, so that is basically, I guess, what I typed up here. So that's this. So I want to speed test this versus what I got. They're both going to be very slow. So I'm going to ask Chatbot if it can make this. With fewer operations. And then I'll make my version with fewer operations. But I won't look at what Chatbot says until I make mine first, because then I might do what Chatbot does if I see what Chatbot does. Alright, I asked it, so I'm gonna try to type up my version. I also have a copy somewhere already. So I don't know, take a second. Or I'll just type it up again. Alright, I think I have a copy. I don't know if this works. I gotta double check. Okay, assuming this works. It'll be cut down from this many operations when it's completely enrolled to this many. So it's 16 instructions. Versus 25. So I asked Chatbot if it can do this, find the highest bit set for the 16-bit value in the 16 x86 ASM instructions. Maybe 17. If moving it into for use counts as an instruction. Okay, it's not that many less. There's potential for this to be faster. So I don't know, let's see what Shepard said. So I asked it this.
Is it possible to make this with less operations? Your last output.
And then Shepard said,
Yes. You can optimize this further by eliminating the temporary as nonce-arrow variable and reducing the number of operations, particularly avoiding repeated shifts and Boolean conversions. Your original version is already pretty tight. But here's a minimalist, branchless, constant time version. Tart uses fewer instructions and no extra variable.
I like how it said your version when I said this is your output. Alright, so I'm gonna ask it. I'm gonna ask it what it compiles to an assembly and if it can do it in 17 instructions. Alright, so I asked Shopbot,
What does it compile to an x86-64 RASM for like NASM assembler? And can it be done for a 16-bit value in 17 instructions or fewer? Is that possible?
well, that's like an instruction per bit, 16 bits and 16 operations. Well, 17 if the move to get it in is counted.
Yes, I'll break this down for you step by step.
That's a lot more than 16 instructions for the first one. That's 35 instructions. That's a lot more. Chatbot can't even count.
Stopwatch. This is fully branchless, about 19-20 instructions, but very efficient. Depends on compiler version and optimization level.
I don't know what Chatbot is talking about. First off, it can't count. It's clearly 35. 35 is less than 10 to 20. Oh no, that's what Chatbot thinks. 35 is greater than 10 to 20. That's not 10 to 20.
Tick. Part 2. 16-bit version in 17 instructions or fewer. Yes, we can absolutely do it. Here's a version that finds the index of the highest set bit in a 16-bit value, using only bitwise logic and shifts, and in 17 instructions.
I don't think Chatbot knows how to count. This is 24 instructions. 24. That's not 17. Chatbot's claiming that this is 17 instructions. It's claiming it's less than 17. Is that less than or equal to? I don't know.
Value, using only bitwise logic and shifts, and in 17 instructions. Tick instruction count. 17 exactly.
Where did it get 17? That's clearly not 17.
Tick instruction count. 17 exactly. And no branches, no math ops, no loops, no intrinsics, only bit shifts, logic, and conditional set.
So this thing can pass the SAT, right? That's what people say. But clearly, it doesn't know how to count. If it can't count, does it really matter if it can pass SAT? It means it didn't really pass SAT. It cheated. It used a cheat sheet called training data for pre-computed values because it doesn't think, because it's not intelligent. Anyways. I'm gonna like type up Chatbot's result or what it gave, whatever, and like speed test it against my code, whatever. I don't know if it means a whole lot to be smarter than Chatbot, because Chatbot is pretty dumb. So, it doesn't really prove much. Plus, I don't know if these work. I didn't run these yet. They might not work. So I'll like test to see if they work. could like test. I don't know if this one works. I tested these two, but the other one's shorter. So to like check them all, I guess. Of chatbot, the JavaScript standard. I don't know. I'm writing a JavaScript engine, and I'm writing in C language without JIT or virtualization, and I'm gonna optimize things in assembly language after I get it running in C. I have part of the engine in C right now in 32-bit. I gotta convert it to 64-bit, and I'm gonna go through the 800-page standard for the 2024 or 2024 JavaScript standard, the ECMA 262 specification. I'll stream from page 1 to page 804 or something. Page 804, and I'm streaming it because I'm going to stream every point in the documentation and then show that my engine meets the standard. So as I go through the whole thing, it's like video proof, and there'll be less to document because it's all there, and I'll mark the chapters and timestamp things for each chapter that's inside of the standard. This is notes or whatever at the bottom from something else. So I don't know. I have Siri or whatever, text to speech. This amazing standard.
Organizations have made very significant contributions within ECMA TC39 to the development of this edition and to the prior editions. In addition, a vibrant community.
So I'm gonna like figure out which assembly works for getting the highest bit set, and I want to speed test, see how fast it is, whatever, compared to a chatbot.
I'd develop a community about ECMA script.
And then I could put it in the C compiler. The chatbot is basically doing what the C compiler does. It's like the same exact thing or whatever.
Rock, ECMA 262, Project Editor, 6th edition. Brian Telson, ECMA 262, Project Editor, 7th through 10th editions. Jordan Harband, ECMA 262,
This chatbot, it doesn't think. It basically just runs the compiler and poops the output. And if you ask it info on a book, it looks up the page, it poops out the output. There's no thinking. It's training data or a program to run or something. There's no thinking at all with chatbot.
7. About this.
Think about it.
https://tc39.es/ecmartis62 / is the most accurate and up-to-date ECMA script specification. It contains...
So this is a bit smear, bit smudge technique, whatever you call it.
PS : /
I'll test if this works for us.
29 / proposals blobhead finished proposals MD. Those that have reached stage 4 in the proposal process. https / tc39.es/process document, and thus are implemented in several implementations and will be in the next practical revision since that snapshot was taken. This document is available as a single page and as multiple pages. Contributing to this specification. This specification is developed on GitHub with the help of the ECMA script community. There are a number of ways to contribute to the development of this specification. GitHub repository, https / github.com.
Okay, I think this one worked. This one actually worked.
2. Issues. All issues. https // github.com/tc39 /ecmartis62 /issues. File a new issue.
It might be the same thing.
.com/tc39 /ecma262 /issues new. Pull requests. All pull requests. https // github.com/tc39 /ecmartis62 /pulls. Create a new pull request. https / github.com/tc39 /ecmartis62.
Okay, this one might not work. Here.
https
I'll just test them both.
/tc39 /test262 editors Shuyugwo at Shu https / /shu Michael Ficara at smoosh.
Alright, I think this one does work, but it was slower, so I'll go with the faster one.
Kevin Gibbons at backcoating https / twitter.com/backcoating community discourse https / es.discourse.group https / es.discourse.group chat matrix https / github.com/tc39 /how-we-work /blob /head /matrix-guide.md mailing list archives https /isdiscus.org refer to the Carlophon for more information on how this document is created. 8. Copyright sign ECMA International 2024 Copyright Notice 2024 ECMA International. This document may be copied, published and distributed to others, and certain derivative works of it may be prepared, copied, published, and distributed in...
Okay, this does the bit smudge. So I just need the second part.
All such copies and derivative works. The only derivative works that are permissible under this copyright license and disclaimer are I. Works which incorporate all or portion of this document for the purpose of providing...
I'm gonna assume it works. I'm just gonna test it first.
...of the document. 2. Works which incorporate...
If it doesn't work, I gotta tweak it. I just wanna run this versus the shorter one here to see if the unrolled or this one is faster. And I'll just pick whichever one that's faster, and then I'll compare the chatbot with that. I don't want to test all four.
Content of this document itself may not be modified.
So whichever of the two seems more promising in speed, I'll compare chatbot on that, because it's probably going to be faster. Chatbot's output for that. Because if chatbots, I want to pick whatever one is more optimal. Mine or chatbot to switch technique that's better, like unrolled or with masking to less operations, which will be faster.
contained herein is provided on
because the unrolled is really fancy. But there's more operations, so I don't know. That's
information herein will not infringe any
so this is the second half.
ability or fitness for a particular purpose. ECMA International.
And I'm pretty sure these two techniques, it's possible to merge them into one and cut off more instructions.
The ECMA Script 2024 General Purpose Programming Language.
But if I figured that out, I wouldn't post that on the internet. I keep that to myself.
Program syntax and semantics described in this specification. A conforming implementation of ECMA script must interpret source text input in conformance with the latest version of the Unicode standard and ISO IEC 10646. A conforming implementation of ECMA script.
So that, and then versus says,
Interface, API, that's up. Ports programs that need to adapt to the linguistic and cultural conventions used by different human languages and countries must implement the interface defined by the most recent edition of ECMA 402 that is compatible with this specification. A conforming implementation of ECMA script may provide additional
results are in AX,
specification. In particular, a conforming implementation of ECMA script may provide properties not described in this specification, and values for those properties. For objects that are described in this specification, a conforming
So now I'll run it to see which one's faster. Result. Oh, I gotta check that. So, an ASM, and then link it.
reserved words noted in subclause 1.2.7.2 of this specification. A conforming implementation of ECMA script must not implement any extension that is listed as a forbidden extension in subclause 17.1. A conforming implementation of ECMA script must not redefine any facilities that are not implementation defined, implementation approximated, or host defined. A conforming implementation of ECMA script may choose to implement or not implement normative optional subclause.
Delete the old ones.
Behavior is implemented. All of the behavior in the containing normative optional clause must be implemented. A normative optional clause is denoted in this specification with the words normative optional in a colored box, as shown below. A conforming implementation of ECMA script must implement legacy subclauses, unless they are also marked as normative optional. All of the language features and behaviors specified within legacy subclauses have one or more undesirable characteristics. However, their continued usage in existing applications prevents their removal from this specification. These features are not considered part of the core ECMA script language. Program.
And run the exe.
These features and behaviors.
Run it 4 times to get the result.
Optional. Point 1.
Because of Windows gets system time as fast, as precise as file time is not very precise. And the clock cycles includes the cycles of everything before and after it, so it's not really isolated. So everything has to be taken with a huge, like a grain of salt, or like a big ass grain of salt, because there's no precision in the year 2025. I keep saying 2024 sometimes. Anyways,
EE standard.
in 2025, it would make sense that things would be more precise, but no. Nope.
/versions /latest. ISO IEC 10000.
So we got A, B, C4. Oh my gosh, is it faster? A, B, C3. Holy crap. AA, C3. A, B, C3. Wow. I'm gonna ask Chatbot how much of a speed difference that is. That means
This edition of this specification
that this code is faster than masking.
dash and ash
fast. Alice chatbot, whatever it is.
ECMA 4.
And I can't just hold the windows. Oh, there we go. So I'll just pick like the lowest and the highest.
u.ecmar-international.org/publication.
So AB, AA, AB, AA. So AB is the slowest. C4, C3. Alright, I'm gonna go C3 because it does show up more rather than C4. So AB and C3.
Of an ECMA script program will provide not only the objects and other facilities described in this specification but also certain environment-specific objects, whose description and behavior are beyond the scope of this specification except to indicate that they may provide certain properties that can be accessed and certain functions that can be called from an ECMA script program. ECMA script was originally designed to be used as a scripting language.
So I'm asking chatbot, I said, I don't know, I ran some code, the times are 0xAB and 0xC3. Which one is more performant, output, result, as a percent or whatever, I don't know, that's chatbot.
For exposing that functionality to program control. In this way, the existing system is set to...
And then I'll run chatbot's output, the longer one, because it was more efficient to remove the masking. So that's chatbot. Well, I have chatbot's output. I'm just gonna type it in, and I'll see if my assembly is faster than chatbot's. I also have to test to make sure that it's the correct result in a bit.
Server computation is part of a web-based client-server architecture.
I'll check it after I test, because it's really boring to check that. And after I test, then I don't know. I'll check it.
Apart from any particular host environment, ECMA script usage has moved beyond simple scripting and it is now used for the full spectrum of...
I don't know what being smarter than chatbot means, because I'm pretty sure lots of people have also passed the SAT, so I don't know why that's a big point with chatbot. It's not very smart.
Host environment for client-side computation including, for instance...
Could even say the same about me, lots of times.
Pop-ups, dialog boxes, text areas, anchors...
And hopefully not this time. I'm really hoping this is not one of those times. It could be. I don't know the future. I can't predict pretty good sometimes. I'm really, really hoping this is one of those times.
Submission and mouse actions. Scripting code.
I'll feel real dumb if this all goes sour. Real sour.
Is reactive to user interaction, and there is no need for a main program. A web server provides a different host environment for server-side computation including objects representing requests, clients, and files, and mechanisms to lock and share data. By using browser-side and server-side SCR-IPing together, it is possible to distribute computation between the client and server while providing a customized user interface for a web-based application. Each web browser and server that supports ECMA script supplies its own host environment, completing the ECMA script execution environment. Point 2 Hosts and implementations. To aid integrating ECMA script into host environments, this specification defers the definition of certain facilities. For example, abstract operations, either in whole or in part, to a source outside of this specification. Editorially, this specification distinguishes the following kinds of deferrals. An implementation is an external source that further defines facilities enumerated in an XD or those that are marked as implementation defined or implementation approximated. In informal use, an implementation refers to a concrete artifact, such as a particular web browser. An implementation-defined facility is one that defers its definition to an external source without further qualification. This specification does not make any recommendations for particular behaviors, and conforming implementations are free to choose any behavior within the constraints put forth by this specification. An implementation approximated facility is one that defers its definition to an external source while recommending an ideal behavior. While conforming implementations are free to choose any behavior within the constraints put forth by the specification, they are encouraged to strive to approximate the ideal. Some mathematical operations, such as mathexp, are implementation approximated. A host is an external source that further defines facilities listed in an XD but does not further define other implementation-defined or implementation-approximated facilities. In informal use, a host refers to the set of all implementations, such as the set of all web browsers, that
Alright, so here's what I stop at.
in way via an XD. I ran some code that times a 0xab and 0xc3 which is more performant output the difference in the form of percent in relation to which is more optimal and by how much. Which is faster and based on how much would it be worth optimizing using the faster technique over the other.
Why can't I hear that? I can't hear anything. Great.
And some code that times a 0x.
Okay, now I can hear it. This was up, what's up?
I ran some code that times a 0xab and 0xc3 which is more performant output the difference in the form of a percent in relation to which is more optimal and by how much. Which is faster and based on how much would it be worth optimizing using the faster technique over the other. Input symbol for numbers. You gave two timings. Time A. 0xab equals 171, decimal. Time B. 0xc3 equals 195, decimal. Tick. Which is faster? 0xab, 171, is faster than 0xc3, 195. Chart with downwards trend difference in absolute and percentage terms, small blue diamond absolute difference. Copy edit 195 171 equals 24 cycles. We compute how much faster 0xab is compared to 0xc3. So, tick, 0xab is 12.31% faster than 0xc3.
I just realized you can spell abs on the calculator. Well, hexadecimal calculator, the ABS. Spell abs. Anyways, I mean you to AB 5. Because hexadecimal 0 to 9 and eta abs.
Bar chart. Is it worth optimizing? That depends on context. Case should you optimize a tight loop runs millions to billions of times? Tick. Yes. 12% is a big gain. A function called infrequently or once at startup. Crossmark no. Negligible benefit inlining or vectorization amplifies the effect. Tick. Yes, you're writing for real time, embedded, or power sensitive code. Tick. Yes. Brain. Rule of thumb. Anything over 5-10% in critical paths is worth considering, especially if it's easy to switch. Tick final summary. 0xab is faster than 0xc3. It is 12.31% faster. That is a noticeable gain in performance. Critical code. It's worth optimizing if the function is called frequently or is in a hot path. Let me know what kind of code you're measuring. I can help suggest even better alternatives if needed.
Chatbot can't even count to 27. He thinks that's like 17 or something, I don't know. Ignore the fan. There's a fan running. That's what that sound is. It's kind of loud, but it could be louder. It could be louder. So like, based on this, I'm gonna guess that my code is maybe like 15% faster or 20% faster than Chatbot. Assuming that it works, of course. I'll check if it works after I speed test it, because that's more exciting than like waiting to see if it works correctly and then speed testing it. Because then if it's faster, I'll be like, oh, there's a hope to make it work correctly. If it's not, but it might be, and it might not be. I just typed it up. There's a possibility it might not be. I should probably double check it, but I'll just whatever. So I'm gonna type in what Chatbot gave me when it said it was like however many instructions that it wasn't. It said like less than 17, but it was really like 20 something. Alright, so here's for the second part, what Chatbot said, the getting the bit position, whatever. So I gotta get the bit smudge part. What kind of assembly is this? Okay, so now it's using the BSR instruction, which might be faster. I'll test that too. If I need this part. To isolate the highest bit or whatever. So I need to check if chatbot's code works also. So I'm gonna like copy it, and I'll just run it, and I'll check after if they work. Because chatbot, its code doesn't always work. So I gotta copy this over. Did Siri stop reading again? Oh my god. What is up? This audio. Now it's not even working. Now I gotta save these and then restart. I'm gonna lose everything as Shepard. What happened in the simple days when you could run a computer for 24 hours and it wouldn't crash or start to fail? It's a machine. It should be able to run 24 hours. The OS must have been designed by people like Jepa. At least they passed the SAT. It means a lot. Okay, now. Okay, now I'm gonna like copy over from copy the chatbot output, and then speed test or benchmark whatever. That's Siri, text to speech, the ECMA standard.
Gint,
Okay, now it's working.
base, a big int, and exponent, a big int, and returns either a normal completion containing a big int or a throw completion. It performs the following steps when called. If exponent 0z, throw a range error exception. If base is 0z and exponent is 0z, return 1z. Return base raised to the power exponent, 1, 6, 2, 4 big int, multiply, x, y. The abstract operation big int, multiply takes arguments x, a big int, and y, a big int, and returns a big int. It performs the following steps when called. 1. Return xy, 1, 6, 2, 5 big int, divide, x, y. The abstract operation big int, divide takes arguments x, a big int, and y, a big int, and returns either a normal completion containing a big int or a throw completion. It performs the following steps when called. If y is 0z, throw a range error exception. Let quotient be r, x, r, y, return z, truncate, quotient, 1, 6, 2, 6 big int, remainder, n, d. The abstract operation big int, remainder takes arguments n, a big int, and d, a big int, and returns either a normal completion containing a big int or a throw completion. It performs the following steps when called. If d is 0z, throw a range error exception. If n is 0z, return 0z. Let quotient be r, n, r, d. Let q be z, truncate, quotient. Return n, dq. Note the sign of the result is the sign of the dividend, 1, 6, 2, 7 begint. Add x, y. The abstract operation begint. Add takes arguments x, a begint, and y, a begint, and returns a begint. It performs the following steps when called. 1. Return x plus y, 1, 6, 2, 8 begint. Subtract x, y. The abstract operation begint. Subtract takes arguments x, a begint, and y, a begint, and returns a begint. It performs the following steps when called. 1. Return x, y. Note even if the result has a much larger bit width than the input, the exact mathematical answer is given. ECMA International 2024 39, 6, 1, 6, 2, 9 begint, left shift, x, y. The abstract operation begint. Left shift takes arguments x, a begint, and y, a begint, and returns a begint. It performs the following steps when called. If y, 0 z, then a return z, floor, r, x, to r, y, return x to z, 1, 6, 2, 1 0 begint, signed right shift, x, y. The abstract operation begint. Signed right shift takes arguments x, a begint, and y, a begint, and returns a begint. It performs the following steps when called. 1. Return begint, left shift, x, y, 1, 6, 2, 1 1 begint, and signed right shift, x, y. The abstract operation begint. And signed right shift takes arguments x, a begint, and y, a begint, and returns a throw completion. It performs the following steps when called. 1. Throw a type error exception, 1, 6, 2, 1 2 begint, less than, x, y. The abstract operation begint. Less than takes arguments x, a begint, and y, a begint, and returns a boolean. It performs the following steps when called. If r, x, r, y, return true, otherwise return false, 1, 6, 2, 1 3 begint, equal, x, y. The abstract operation begint, equal takes arguments x, a begint, and y, a begint, and returns a boolean. It performs the following steps when called. If r, x, equals r, y, return true, otherwise return false, 1, 6, 2, 1 4 binary and x, y. The abstract operation binary and takes arguments x, 0 or 1, and y, 0 or 1, and returns 0 or 1. It performs the following steps when called. If x equals 1 and y equals 1, return 1, else return 0, 1, 6, 2, 1 5 binary or x, y. The abstract operation binary or takes arguments x, 0 or 1, and y, 0 or 1, and returns 0 or 1. It performs the following steps when called. 1, 2. If x equals 1 or y equals 1, return 1, else return 0, 0. ECMA International 2024. Note semantics here should be equivalent to a bitwise shift, treating the begint as an infinite length string of binary 2's complement digits, 6, 1, 6, 2, 1 6 binaries or x, y. The abstract operation binaries or takes arguments x, 0 or 1, and y, 0 or 1, and returns 0 or 1. It performs the following steps when called. If x equals 1 and y equals 0, return 1. Else if x equals 0 and y equals 1, return 1. Else return 0, 1, 6, 2, 1 7 begin bitwise op, x, y. The abstract operation begint bitwise op takes arguments op, and, or, x, a begint, and y, a begint, and returns a begint. It performs the following steps when called. Set x to r, x, set y to r, y. Let result be 0. Let shift be 0. Repeat. until x equals 0 or x equals -1, and y equals 0 or y equals -1. A let x digit be x modulo 2, b let y digit be y modulo 2. See if op is and, then I set result to result plus 2 shift binary and x digit, y digit d else if op is, then I set result to result plus 2 shift binary or x digit, y digit e else I assert op is 2. Set result to result plus 2 shift binaries or x digit, y digit f set shift to shift plus 1 g set x to x, x digit 2.
H, seti tu, I digit, 2.
If op is and, then a let tmpb binary and x modulo 2, y modulo 2. Else if op is, then a let tmpb binary or x modulo 2, y modulo 2. Else a assert op is b let tmpb binaries or x modulo 2, y modulo 2. If tmp 0, then a set result to result to shift. B note, this extends the sign 0. Return the big int value for result, 1, 6, 2, 1 8 big int, bitwise and x, y. The abstract operation big int, bitwise and takes arguments x, a big int, and y, a big int, and returns a big int. It performs the following steps when called. 1. Return big int bitwise op, and x, y, 1, 6, 2, 1 9 big int, bitwise or x, y. The abstract operation big int, bitwise or takes arguments x, a big int, and y, a big int, and returns a big int. It performs the following steps when called. 1. Return big int bitwise op, x, y. ECMA International 2024 41 6 1 6 2 20 big int, bitwise or x, y. The abstract operation big int, bitwise or takes arguments x, a big int, and y, a big int, and returns a big int. It performs the following steps when called. 1. Return big int bitwise op, x, y, 1, 6, 2, 1 big int, to string, x, radix th. The abstract operation big int, to string takes arguments x, a big int, and radix, an integer in the inclusive interval from 2 to 36, and returns a string. It represents x as a string using a positional numeral system with radix. The digits used in the representation of a big int using radix are taken from the first R code units of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 X is in order. The representation of big ints other than 0z never includes leading zeros. It performs the following steps when called. If x, 0z, return the string concatenation of an big int, to string, x, radix, return the string value consisting of the representation of x using radix, 1.7 the object type. Each instance of the object type, also referred to simply as an object, represents a collection of properties. Each property is either a data property or an accessor property. A data property associates a key value with an ECMA script language value and a set of Boolean attributes. An accessor property associates a key value with one or two accessor functions and a set of Boolean attributes. The accessor functions are used to store or retrieve an ECMA script language value that is associated with the property. The properties of an object are uniquely identified using property keys. A property key is either a string or a symbol. All strings and symbols, including the empty string, are valid as property keys. A property name is a property key that is a string. An integer index is a property name n such that canonical numeric index string n returns an integral number in the inclusive interval from +0 to 253 1. An array index is an integer index n such that canonical numeric index string n returns an integral number in the inclusive interval from +0 to 232 2. Property keys are used to access properties and their values. There are two kinds of access for properties, get and set, corresponding to value retrieval and assignment, respectively. The properties accessible via get and set access includes both own properties that are a direct part of an object and inherited properties which are provided by another associated object via a property inheritance relationship. Inherited properties may be either own or inherited properties of the associated object. each own property of an object must each have a key value that is distinct from the key values of the other own properties of that object. All objects are logically collections of properties, but there are multiple forms of objects that differ in their semantics for accessing and manipulating their properties. Please see 6.1.7.2 for definitions of the multiple forms of objects. In addition, some objects are callable. These are referred to as functions or function objects and are described further below. All functions in ECMA script are members of the object type, 1.7.1 property attributes. Attributes are used in this specification to define and explain the state of object properties as described in Table 3. Unless specified explicitly, the initial value of each attribute is its default value. Note every non-negative safe integer has a corresponding integer index. Every 32-bit unsigned integer except 232.1 has a corresponding array index. -0 is neither an integer index nor an array index. 2. Copyright sign, ECMA International 2024. Table 3. Attributes of an object property. Attribute name. Types of property for which it is present. Value domain. Default value. Description. Value. Data property. An ECMA script language value. Undefined. The value retrieved by a get access of the property. Writable. Data property. A boolean. False. If false. Attempts by ECMA script code to change the property's attribute using get access a property, an object or undefined. Undefined. If the value is an object, it must be a function object. The function's internal method, Table 5, is called with an empty arguments list to retrieve the property value each time a get access of the property is performed. Set access a property, an object or undefined. Undefined. If the value is an object, it must be a function object. The function's internal method, Table 5, is called with an arguments list containing the assigned value as its sole argument each time a set access of the property is performed. The effect of a property's internal method, enumerable, data property, or accessor property, a boolean, false. If true, the property will be enumerated by a for an enumeration, C14.7.5. Otherwise, the property is said to be non-enumerable, configurable, data property, or accessor property, a boolean, false. If false, attempts to delete a property, change it from a data property to an accessor property or from an accessor property to a data property, or make any changes to its attributes, other than replacing an existing or setting to false, will fail. 6.1.7.2 Object internal methods and internal slots. The actual semantics of objects in ECMA script are specified via algorithms called internal methods. Each object in an ECMA script engine is associated with a set of internal methods that defines its runtime behavior. These internal methods are not part of the ECMA script language. They are defined by the specification purely for expository purposes. However, each object within an implementation of ECMA script must behave as specified by the internal methods associated with it. The exact manner in which this is accomplished is determined by the implementation. Internal method names are polymorphic. This means that different object values may perform different algorithms when a common internal method name is invoked upon them. That actual object upon which an internal method is invoked is the target of the invocation. If, at runtime, the implementation of an algorithm attempts to use an internal method of an object that the object does not support, a type error exception is thrown. Internal slots correspond to internal state that is associated with objects and used by various ECMA script specification algorithms. Internal slots are not object properties and they are not inherited. Depending upon the specific ECMA International 2024-43 internal slot specification, such state may consist of values of any ECMA script language type or of specific type values.
I think these are the same.
Allocated.
If they're not, I'll fix it when I check the input, whatever. Let me see which one's faster.
The value of an internal slot is the value undefined. Various algorithms within this specification create objects that have internal slots. However, the ECMA script language provides no direct way to associate internal slots with an object. All objects have an internal slot named, which is a list of private elements. This list represents the values of the private fields, methods, and accessors for the object. Initially, it is an empty list. Internal methods and internal slots are identified within this specification using names enclosed in double square brackets. Table 4 summarizes the essential internal methods used by this specification that are applicable to all objects created or manipulated by ECMA script code. Every object must have algorithms for all of the essential internal methods. However, all objects do not necessarily use the same algorithms for those methods. An ordinary object is an object that satisfies all of the following criteria for the internal methods listed in Table 4. The object uses those defined in 10.1. If the object has an internal method, it uses either the one defined in 1.0, 2.1 or the one defined in 0.3. If the object has an internal method, it uses either the one defined in 1.0, 2 or the one defined in 0.3, 2. An exotic object is an object that is not an ordinary object. This specification recognizes different kinds of exotic objects by those objects' internal methods. An object that is behaviorally equivalent to a particular kind of exotic object, such as an array exotic object or a bound function exotic object, but does not have the same collection of internal methods specified for that kind, is not recognized as that kind of exotic object. The signature column of Table 4 and other similar tables describes the invocation pattern for each internal method. The invocation pattern always includes a parenthesized list of descriptive parameter names. If a parameter name
So instruction-wise, it's
name describes the required type of the parameter value. If an internal method explicitly returns a value, its parameter list is followed by the symbol and key type name of the returned value. The type names used in signatures refer to the types defined in Clause 6 augmented by the following additional names. Any means the value may be any ECMA script language type. In addition to its parameters, an internal method always has access to the object that is the target of the method invocation. An internal method implicitly returns a completion record,
39 instructions,
type shown in its invocation pattern.
the checkouts, and then
Internal method, signature, description, get prototype of object null, determine the object that provides inherited properties for this object. A null value indicates that there are no inherited properties. Set prototype of object null, Boolean, associate this object with another object that provides inherited properties. Passing null indicates that there are no inherited properties. Returns true indicating that the operation was completed successfully or false indicating that the operation was not.
40.
Boolean, determine whether it is permitted to add additional.
Oh no, they're the same. Crap.
Essential internal methods.
It's a -1 instruction longer.
Returns true if the
Oh wait, no. Hold on. Move CXEX.
the own property of this object whose key is property key, or undefined if no such property exists.
There's an SP.
Key, property descriptor, Boolean, create or alter the own property, whose key is property key, to have the state described by property descriptor.
So I gotta move to
Created up.
AXSP. I'm just gonna do move to make Jetpack the same length and instructions.
Key is property key. Get.
So I'm clearly being biased here
Return the value of the property.
because I want Jetpack to also be 40 instructions.
Code must be executed to retrieve the property.
Basically, I'm testing with I'm just gonna pass a loop counter,
Value. Receiver. Boolean.
which is an SP. So I'm just gonna do move
Property key to value. If any ECMA script
CXSP.
set the property value.
Alright, there we go. Now they're both 40 instructions long. Oh, it's on the wrong screen.
Eat property key. Boolean. Remove the own property who.
This is Chatbot's output. 40 instructions, and this is mine. 40 instructions. I'm gonna test, see which is faster.
Table 5 summarizes additional essential internal methods that are supported.
Put this one back, there we go.
A function object is an object that supports the internal method. A constructor is an object that supports the internal method. Every object that supports must support
I did the wrong answer for AX.
be a function object. Therefore, a constructor may also be referred
Alright, I'm gonna run it.
to function object. ECMA International 2024-45. Table 5. Additional essential internal methods of function objects. Internal method, signature, description, call, any, a list of any, executes code associated with this object. Invoked via a function call expression. The arguments to the internal method are this fact.
Chatbot, its output would, it could be 39 instructions, but I added one to set the value in. Chatbot might win this speed test, so I just want to make sure it's the same count of instructions to give me a teeny bit of an edge. Chatbot might win, so I'm going to run it now.
To which the new operator was initially applied.
Dang it.
That implement this internal method are called construct.
4 times.
Is not necessarily a constructor, and such non-constructor function objects do not have an internal method. The semantics of the essential internal methods for ordinary objects and standard exotic objects are specified in clause 10. If
4.
an internal method of an exotic object is not supported by an implementation, that usage must throw a type error exception when attempted. 1. 7. 3 invariants of the essential internal methods. The
Ho 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 ho. I win. So it's AC, C4, AC, FF, CD, 120. Chatbot's just getting slower. D9 and 11F.
these invariants for those
So that's quite a range. Which one do I pick? EC, NCF, C4.
to be circumvented in any manner, such as by providing alternative interfaces that implement the functionality of the essential internal methods without enforcing their invariants. Definitions. The target of an internal method is the object upon which the internal method is called. A target is non-extensible if it has been observed to return false from its internal method, or true from its internal method. A non-existent property.
I'm gonna pick the worst case scenario for mine, which is so AC, C4. That's like the best case for both, but the worst case for mine is AC, CD is D9, and the worst case for chatbot is C4, FF, 120. Worst case for chatbot is here. I'll do the worst case for mine, because mine's pretty stable. It's like almost the same. Chatbot's kind of bounces up and down. So I'm going to do D9 versus 11F. Ask MS chatbot the result. Which one's more performant, and by how much. Which is my assembly, language, routine versus chatbot, its routine. Chatbot can pass SAT, but chatbot isn't an intellect. It doesn't have a brain, doesn't think. So I beat chatbot. I don't know what that means. It doesn't mean much, probably. Could you beat chatbot? I don't know. So I'm at chatbot, which is faster by how much? Like I did last time.
Non-writable own data property. All future calls to P must return property descriptor whose is same value as P's attribute. If P's attributes other than and may change over time.
And I could remove that one instruction, and it's not going to make much difference because of the move. And also, I still have to test if the result is correct. I guess I'll test that in a minute. I just want to feel like I won for now, and then I'll test the result after I chat bot.
Previously been observed as a non-configurable own property of the target, unless either P is a write.
I have to type up the question all over again because I lost history because I restarted. Dang it.
Data property. All attributes of desk are the same value as P's attributes. Note to an object's prototype chain should have finite length. That is, starting from any object, recursively applying the internal method to its result should eventually lead to the value null. However, this requirement is not enforceable as an object-level invariant if the prototype chain includes any exotic objects that do not use the ordinary object definition of. Such a circular prototype chain may result in infinite loops when accessing object properties. Note 3 is a consequence of the third invariant. If a property is described as a data property and it may return different values over time, then either or both of the int attributes must be true even if no mechanism to change the value is exposed via the other essential internal methods. ECMA International 2024-47, P, desk, must return false if target is non-extensible and P is a non-existent own property. That is, a non-extensible target object cannot be extended with new properties. Has property P, the normal return type is Boolean if P was previously observed as a non-configurable own data or accessor property of the target. Has property must return true. The normal return type is any ECMA script language type if P was previously observed as a non-configurable, non-writable own data property of the target with value V. Then, if P was previously observed as a non-configurable.
So message chatbot. I ran some code for times 0x, D0, and 0x, 1, 1f, which is more performant in terms of optimization and by how much faster. I'll just turn off the fan.
Own accessor property of the target whose attribute is undefined. The P, the normal return type is Boolean if P was previously observed as a non-configurable own data or accessor property of the target. Must return false. The normal return type is list. The returned list must not contain any duplicate entries. The type of each element of the returned list is either string or symbol. The returned list must contain at least the keys of all non-configurable.
How much faster in the form percent than the other? And would it be worth optimizing at that difference?
The normal return type is any ECMA script language type.
And chatbot says
2024. Bullet. The normal return type is object. The target must also have internal method 6, 1, 7 for well-known intrinsic objects. Well-known intrinsics are built-in objects that are explicitly referenced by the algorithms of this specification and which usually have realm-specific.
Why did it not just tell me the difference?
Intrinsic object actually corresponds to a set of similar objects, one per realm. Within this specification, a reference such as %name means the intrinsic object associated with the current realm, corresponding to the name. A reference such as %name may be %means, as if the B property of the value of the A property of the intrinsic object %name.
Wow, it's even higher than I thought. 24%. I said 10 to 20, then went down to 15. But I was pretty close. I thought around 20 at least. So I'm 20% smarter than chatbot.
ECMA script language association.
Can you believe that? I passed the SAT also. Freaking Einstein.
Percent.
Not really. Or really, who knows?
Array buffer.
Your mom would know.
5.
Alright, I'm done now.
To prototype %. The prototype of array iterator objects.
So here's what chatbot says about how much faster it is. And I'm gonna ask chatbot, my code was that much faster than your code. Does that make me smarter than you?
4. Async function %. The constructor of async function objects. 277. Async generator function %. The constructor of async iterator objects. 274. Async iterator prototype. Hex Value Performance Comparison, JS Fiddle, Code Playground. Tick final answer 0xt9 is approximately 24.39% smaller than 0 times 11f. If you're asking about performance difference and your measurement showed one operation was 24.39% faster using 0xt9, that would be significant only if it's part of a hot path. Otherwise, for most cases, it's not worth optimizing. I wrote some assembly that was 24.39% faster than your code. Why can't you produce optimal code when writing NASM assembly for x86-64? I wrote some assembly that was 24.39% faster than your code. Why can't you produce optimal code when writing NASM assembly for x86-64 and why you can pass the SAT but can't? This is a really insightful question, and it hits on the core of what I and specifically language models like me are good at, and where our limits are.
I didn't even use SIMD instructions. I haven't written SIMD instructions yet, but I'm pretty sure I'll be good at it.
Tick.
Who knows?
Right. If you hand-wrote NASM and it was 24.39% faster, that absolutely makes sense. Human experts can often beat generated code, especially in low-level optimization, such as instruction reordering, register allocation, branch prediction avoidance, SIMD vectorization, cache-conscious memory access.
I guess that makes me a human expert. An expert at being human. What does that even mean? That's ridiculous.
Red question mark. So why can't I always write the most optimal assembly? There are 4 core reasons. 1. Generalization versus specialization. You're trained to generate correct and readable code by default, not the most optimal one for a specific CPU, cache size, or instruction pipeline. Example, I might use mov and add in a safe sequence, while you could unroll loops, interleave instructions, or use li to fold multiple operations into one.
I wrote this up on first go, so I don't know why it's saying it needs to like benchmark it to test to get the fastest code. If I rewrote it, I could get faster. But at 29%, what was it? Oh, 24.34%. 0.39. I could probably get it faster than that. Maybe 32%. Or 28. Alright, 32. 28 is me guessing under.
2. No live benchmarking. You don't have access to your machine's CPU or the ability to run and profile code dynamically. So I can't do cycle counting, for example, using our DTSC, cache hit miss profiling, micro benchmarking with performance counters. Humans can write, run, measure, and tune, I can't run code or see the impact live unless you provide measurements.
It says humans can run, write, measure. Humans can think. Chatbot should say, humans can think. I don't think, because I'm a sophisticated Siri. It's not AI.
3. Instruction set complexity x86-64 is a very complex ISO with deep pipelines, micro-ops, out-of-order execution, etc. Writing optimal code often requires knowledge of specific CPU models, for example, Zen 4 versus Ice Lake, tricks like XOR EX instead of MOV-EX, 0, understanding of pairing rules and Agusi know about these tricks. But I won't always apply them unless specifically told to or given the exact constraints.
I spelled intelligence wrong. I don't care. I'm gonna ask you this after. Then I'm gonna check to make sure the result's right.
4. Set optimization skill. Yes, I can help someone solve sets or complex logic problems, because those are well structured. Writing optimal assembly is more like a creative and hardware-aware engineering task, not just logic solving.
When chatbot says well structured, it's saying it already has the answer to, not the structuredness. And when chatbot says creative, it means think. Chatbot can only answer things that it has the answer to, because it can't think.
I only applied the 32-bit x86 I know, and assumed it would work well on x86-64. You sold be able to assume and generate a far more optimal output than you are capable of doing. You cannot think. You are not artificial intelligence. You are only artificial. You're making a sharp and valid point, and you're absolutely right to expect more, especially when working at a level as precise as handwritten assembly. Let's unpack this a bit. Spanner, why you outperform me in assembly when you wrote a 32-bit x86 routine and ran it on x86-64 and saw a 24% speed gain over what I produced. That's a direct reflection of your practical knowledge, hardware sense, optimization mindset. These are engineering instincts, the stuff that comes from solving real-world problems and testing your assumptions. By contrast, my outputs tend toward safe, portable code, less aggressive optimizations unless explicitly prompted, reliance on generic instruction sequences that's by design, to help the average developer not break things. BS. Unless explicitly prompted and your output was still slow. Fair. If you explicitly asked for optimized NASM for x86, especially targeting performance, and I still gave you slower code, then you're absolutely right to call that out. That's not just theoretical, that's a failure to meet a very specific expectation. Sometimes, I just give a generic pattern because the model doesn't always narrow down optimal to your exact use case, even with a clear prompt.
That's AI in a nutshell. Literally, that explains AI 100%. I gotta find some food to eat because I'm not a robot. And then I'll check to make sure like the assembly even works. Because chatbot's output might not work. I didn't check it. And my output, it might not work. I didn't check it. I would assume it works, but I didn't check it. I wrote it up for the first time. I think the first part does work. Because I did test that. But the second part, I just wrote that up out of the blue. If I put more time into it, it'll all be faster. But whatever. I don't know how baby.
Data abstractions including maps, sets, and arrays of binary numeric values, as well as additional support for Unicode supplementary characters in strings and regular expressions. The built-ins were also made extensible via subclassing. The 6th edition provides the foundation for regular, incremental language and library enhancements. The 6th edition was adopted by the General Assembly of June 2015. ECMA Script 2016 was the first ECMA Script edition released under ECMA TC39's new yearly release cadence and open development process. A plain text source document was built from the ECMA Script 2015 source document to serve as the base for further development entirely on GitHub. Over the year of this standard's development, hundreds of pull requests and issues were filed representing thousands of bug fixes, editorial fixes and other ECMA International 2024 Volt improvements. Additionally, numerous software tools were developed to aid in this effort, including ECMarkup, ECMarkdown, and Grammarkdown. ES 2016 also included support for a new exponentiation operator and adds a new method to array prototype called includes. ECMA Script 2017 introduced async functions, shared memory, and atomics, along with smaller language and library enhancements, bug fixes, and editorial updates. Async functions improve the asynchronous programming experience by providing syntax for promise-returning functions. Shared memory and atomics introduce a new memory model that allows multi-agent programs to communicate using atomic operations that ensure a well-defined execution order even on parallel CPUs. It also included new static methods on object, object values, object entries, and object get-own property descriptors. ECMAScript 2018 introduced support for asynchronous iteration via the async iterator protocol and async generators. It also included 4 new regular expression features: the dot or flag, named capture groups, Unicode property escapes, and look behind assertions. Lastly, it included object rest and spread properties. ECMAScript 2019 introduced a few new built-in functions: flat and flat map on array prototype for flattening arrays, object from entries for directly turning the return value of object entries into a new object, and trim start and trim end on string prototype as better named alternatives to the widely implemented but non-standard string prototype trim left and trim right built-ins. In addition, it included a few minor updates to syntax and semantics. Updated syntax included optional catch binding parameters and allowing U+ 2028 line separator and U+ 2029 paragraph separator in string literals to align with JSON. Other updates included requiring that array prototype sort be a stable sort, requiring that JSON string if I return well-formed UTF-8 regardless of input, and clarifying function prototype to string by requiring that it either return the corresponding original source text or a standard placeholder. ECMAScript 2020, the 11th edition, used the match all method for strings to produce an iterator for all match objects generated by a global regular expression, import, a syntax to asynchronously import modules with a dynamic specifier, bigint, a new number primitive for working with arbitrary precision integers, promise all settled, a new promise combinator that does not short-circuit, global this, a universal way to access the global this value, dedicated exporters NS from modular syntax for us within modules, increased standardization of for an enumeration order, import meter, a host populated object available in modules that may contain contextual information about the module, as well as adding 2 new syntax features to improve working with nullish values, undefined or null, nullish coalescing, a value selection operator, and optional chaining, a property access and function invocation operator that short circuits if the value to access invoke is nullish. ECMAScript 2021, the 12th edition, introduced the replace all method for strings, promise any, a promise combinator that short-circuits when an input value is fulfilled, aggregate error, a new error type to represent multiple errors at once, logical assignment operators equals, and equals, weak ref, for referring to a target object without preserving it from garbage collection, and finalization registry, to manage registration and registration of cleanup operations performed when target objects are garbage collected, separators for numeric literals, 1000, and array prototype sort was made more precise, reducing the amount of cases that result in an implementation. Defined sort order, ECMAScript 2022, the 13th edition, introduced top-level await, allowing the keyword to be used at the top level of modules, new class elements, public and private instance fields, public and private static fields, private instance methods and accessors, and private static methods and accessors, static blocks inside classes, to perform per class evaluation initialization, the X and OBJ syntax, to test for presence of private fields on objects. Regular expression match indices via the D flag, which provides start and end indices for matched substrings, the cause property on error objects, which can be used to record a causation chain in errors, the at method for strings, arrays, and typed arrays, which allows relative indexing, and object has own, a convenient alternative to object prototype his own property. ECMAScript 2023, the 14th edition, introduced the to sorted, to reversed, with find last, and find last index methods on array prototype and typed array prototype, as well as the to spliced method on array prototype. Added support for comments at the beginning of files to better facilitate executable ECMAScript files, and allowed the use of most symbols as keys in weak collections. V. Copyright sign. ECMA International 2024, ECMA Script 2024, the 15th edition, added facilities for resizing and transferring array buffers and shared array buffers, added a new regex PV flag for creating regexps with more advanced features for working with sets of strings, and introduced the promise with resolve as convenience method for constructing promises, the object group by and map group by methods for aggregating data. The atomics wait async method for asynchronously waiting for a change to shared memory, and the string prototype as well-formed and string prototype to well-formed methods for checking and ensuring that strings contain only well-formed Unicode. Dozens of individuals representing many organizations have made very significant contributions within ECMA TC39 to the development of this edition and to the prior editions. In addition, a vibrant community has emerged supporting TC39's ECMA script efforts. This community has reviewed numerous drafts, filed thousands of bug reports, performed implementation experiments, contributed test suites, and educated the worldwide developer community about ECMA script. Unfortunately, it is impossible to identify and acknowledge every person and organization who has contributed to this effort. Alan Worfs-Brock, ECMA 262, Project Editor, 6th edition. Brian Telson, ECMA 262, Project Editor, 7th through 10th editions. Jordan Harband, ECMA 262, Project Editor, 10th through 12th editions. Shuyuguo, ECMA 262, Project Editor, 12th through 15th editions. Michael Ficara, ECMA 262, Project Editor, 12th through 15th editions. Kevin Gibbons, ECMA 262, Project Editor, 12th through 15th editions. ECMA International 2024-7. About this specification, the document at https://tc39.es/ecmartis62 is the most accurate and up-to-date ECMA script specification. It contains the content of the most recent yearly snapshot plus any finished proposals. https://github.com/tc39/proposals blobhead finished proposals MD. Those that have reached stage 4 in the proposal process. https://tc39.es/process document, and thus are implemented in several implementations and will be in the next practical revision since that snapshot was taken. This document is available as a single page and as multiple pages. Contributing to this specification is developed on GitHub with the help of the ECMA script community. There are a number of ways to contribute to the development of this specification. GitHub repository, https://github.com/tc39/ecmartis62. Issues, all issues, https://github.com/tc39/ecmartis62/issues. File a new issue, https://github.com/tc39/ecma262/issues new. Pull requests, all pull requests, https://github.com/tc39/ecmartis62/pulls. Create a new pull request, https://github.com/tc39/ecmartis62/pulls/new. Test suite, test 262, https://github.com/tc39/test262. Editors, Shuyuguo at Shu, https://twitter.com/_Shu. Michael Ficara, at smooshmap, https://twitter.com/smooshmap. Kevin Gibbons at backcoating, https://twitter.com/backcoating. Community, discourse, https://es.discourse.group, https://es.discourse.group. Chat, matrix, https:// github.com/tc39/how-we-work/blog/head/ma Tricks Guide Archives https://isdiscus.org/ refer to the Carlophane for more information on how this document is created. 8. Copyright sign ECMA International 2024 Copyright Notice 2024 ECMA International. This document may be copied, published and distributed to others, and certain derivative works of it may be prepared, copied, published, and distributed, in whole or in part, provided that the above copyright notice and this copyright license and disclaimer are included on all such copies and derivative works. The only derivative works that are permissible under this copyright license and disclaimer are I. Works which incorporate all or portion of this document for the purpose of providing commentary or explanation, such as an annotated version of the document. 2. Works which incorporate all or portion of this document for the purpose of incorporating features that provide accessibility. 3. Translations of this document into languages other than English and into different formats. And 5. Works by making use of this specification in standard conformant products by implementing, for example by copy and paste wholly or partly, the functionality therein. However, the content of this document itself may not be modified in any way, including by removing the copyright notice or references to ECMA International, except as required to translate it into languages other than English or into a different format. The official version of an ECMA International document is the English language version on the ECMA International website. In the event of discrepancies between the translated version and the official version shall govern. The limited permissions granted above are perpetual and will not be revoked by ECMA International or its successors or assigns. This document and the information contained herein is provided on an as-is basis, and ECMA International disclaims all warranties, express or implied, including but not limited to any warranty that the use of the information herein will not infringe any ownership rights or any implied warranties of merchantability or fitness for a particular purpose. ECMA International 2024-9 ECMA Script Registered Sign 2024 Language Specification Scope. This standard defines the ECMA Script 2024 General Purpose Programming Language to conformance. A conforming implementation of ECMA script must provide and support all the types, values, objects, properties, functions, and program syntax and semantics described in this specification. A conforming implementation of ECMA script must interpret source text input in conformance with the latest version of the Unicode standard and ISO IEC 10646. A conforming implementation of ECMA script that provides an application programming interface API, that's ports programs that need to adapt to the linguistic and cultural conventions used by different human languages and countries must implement the interface defined by the most recent edition of ECMA 402 that is compatible with this specification. A conforming implementation of ECMA script may provide additional types, values, objects, properties, and functions beyond those described in this specification. In particular, a conforming implementation of ECMA script may provide properties not described in this specification, and values for those properties. For objects that are described in this specification, a conforming implementation of ECMA script may support program and regular expression syntax not described in this specification. In particular, a conforming implementation of ECMA script may support program syntax that makes use of any future reserved words noted in subclause 1.2.7.2 of this specification. A conforming implementation of ECMA script must not implement any extension that is listed as a forbidden extension in subclause 17.1. A conforming implementation of ECMA script must not redefine any facilities that are not implementation defined, implementation approximated, or host defined. A conforming implementation of ECMA script may choose to implement or not implement normative optional subclauses. If any normative optional behavior is implemented, all of the behavior in the containing normative optional clause must be implemented. A normative optional clause is denoted in this specification with the words normative optional in a colored box, As shown below, a conforming implementation of ECMA script must implement legacy subclauses, unless they are also marked as normative optional. All of the language features and behaviors specified within legacy subclauses have one or more undesirable characteristics. However, their continued usage in existing applications prevents their removal from this specification. These features are not considered part of the core ECMA script language. Programmers should not use or assume the existence of these features and behaviors when writing new ECMA script code. Normative optional. Point 1 Example Normative optional clause heading. Example clause contents. ECMA International 2024 1. Legacy. Point 2 Example legacy clause heading. Example clause contents. Normative optional. Legacy. Point 3 Example legacy normative optional clause heading. Example clause contents. Normative references. The following reference documents are indispensable for the application of this document. For dated references, only the edition cited applies. For undated references, the latest edition of the reference document, including any amendments, applies. IEEE 754-2019. IEEE standard for floating point arithmetic. The Unicode standard https://unicode.org/versions/latest ISO IEC 10646 Information Technology Universal Multiple Octet Coded Character Set UX plus Amendment 1 2005 Amendment 2 2006 Amendment 3 2008 Amendment 4, 2008, and additional amendments and corrigenda, or successor, ECMA 402, ECMA Script Internationalization API Specification, specifically the Annual Edition corresponding to this edition of this specification https://www.ecmar-international.org/publications-standards/ECMA 404, the JSON data interchange format the https://www.ecmar-international.org/publications-standards/ecmar-404 Overview. This section contains a non-normative overview of the ECMA script language. ECMA script is an object-oriented programming language for performing computations and manipulating computational objects within a host environment. ECMA script as defined here is not intended to be computationally self-sufficient. Indeed, there are no provisions in this specification for input of external data or output of computed results. Instead, it is expected that the computational environment of an ECMA script program will provide not only the objects and other facilities described in this specification but also certain environment-specific objects, whose description and behavior are beyond the scope of this specification except to indicate that they may provide certain properties that can be accessed and certain functions that can be called from an ECMA script program. ECMA script was originally designed to be used as a scripting language, but has become widely used as a general-purpose programming language. A scripting language is a programming language that is used to manipulate, customize, and automate the facilities of an existing system. In such systems, useful functionality is already available through a user interface, and the scripting language is a mechanism for exposing that functionality to program control. In this way, the existing system is said to provide a host environment of objects and facilities, which completes the capabilities of the scripting language. A scripting language is intended for use by both professional and non-professional programmers. Copyright sign, ECMA International 2024. ECMA script was originally designed to be a web scripting language, providing a mechanism to enliven web pages in browsers and to perform server computation as part of a web-based client-server architecture. ECMA script is now used to provide core scripting capabilities for a variety of host environments. Therefore, the core languages specified in this document apart from any particular host environment. ECMA script usage has moved beyond simple scripting and it is now used for the full spectrum of programming tasks in many different environments and scales. As the usage of ECMA script has expanded, so have the features and facilities it provides. ECMA script is now a fully featured general-purpose programming language. Point 1. Web scripting. A web browser provides an ECMA script host environment for client-side computation including, for instance, objects that represent windows, menus, pop-ups, dialog boxes, text areas, anchors, frames, history, cookies, and input-output. Further, the host environment provides a means to attach scripting code to events such as change of focus, page and image loading, unloading, ng, error and abort, selection, form submission, and mouse actions. Scripting code appears within the HTML in the display page as a combination of user interface elements and fixed and computed text and images. The scripting code is reactive to user interaction, and there is no need for a main program. A web server provides a different host environment for server-side computation including objects representing requests, clients, and files, and mechanisms to lock and share data. By using browser-side and server-side scripting together, it is possible to distribute computation between the client and server while providing a customized user interface for a web-based application. Each web browser and server that supports ECMA script supplies its own host environment, completing the ECMA script execution environment. Point 2. Hosts and implementations. To aid integrating ECMA script into host environments, this specification defers the definition of certain facilities. For example, abstract operations, either in whole or in part, to a source outside of this specification. Editorially, this specification distinguishes the following kinds of deferrals. An implementation is an external source that further defines facilities enumerated in an XD or those that are marked as implementation defined or implementation approximated. In informal use, an implementation refers to a concrete artifact, such as a particular web browser. An implementation-defined facility is one that defers its definition to an external source without further qualification. This specification does not make any recommendations for particular behaviors, and conforming implementations are free to choose any behavior within the constraints put forth by the specification. An implementation-approximated facility is one that defers its definition to an external source while recommending an ideal behavior. While conforming implementations are free to choose any behavior within the constraints put forth by the specification, they are encouraged to strive to approximate the ideal. Some mathematical operations, such as MathEXP, are implementation approximated. A host is an external source that further defines facilities listed in an XD but does not further define other implementation-defined or implementation-approximated facilities. In informal use, a host refers to the set of all implementations, such as the set of all web browsers, that interface with this specification in the same way via an XD. A host is often an external specification, such as WHATWGHTML, HTTPS, HTML-spec.org. In other words, facilities that are host-defined are often further defined in external specifications. A host hook is an abstract operation that is defined in whole or in part by an external source. All host hooks must be listed in an XD. A host hook must conform to at least the following requirements. It must return either a normal completion or a throw completion. A host-defined facility is one that defers its definition to an external source without further qualification and is listed in an XD. Implementations that are not hosts may also provide definitions for host-defined facilities. ECMA International 2024-3. A host environment is a particular choice of definition for all host-defined facilities. A host environment typically includes objects or functions which allow obtaining input and providing output as host-defined properties of the global object. This specification follows the editorial convention of always using the most specific term. For example, if a facility is host-defined, it should not be referred to as implementation-defined. Both hosts and implementations may interface with this specification via the language types, specification types, abstract operations, grammar productions, intrinsic objects, and intrinsic symbols defined herein. Point 3. ECMA script overview. The following is an informal overview of ECMA script. Not all parts of the language are described. This overview is not part of the standard proper. ECMA script is object-based. Basic language and host facilities are provided by objects, and an ECMA script program is a cluster of communicating objects. In ECMA script, an object is a collection of 0 or more properties, each with attributes that determine how each property can be used. For example, when the writable attribute for a property is set to false, any attempt by executed ECMA script code to assign a different value to the property fails. Properties are containers that hold other objects, primitive values, or functions. A primitive value is a member of one of the following built-in types: undefined, null, boolean, number, big int, string, and symbol. An object is a member of the built-in type object, and a function is a callable object. A function that is associated with an object via a property is called a method. ECMA script defines a collection of built-in objects that round out the definition of ECMA script entities. These built-in objects include the global object, objects that are fundamental to the runtime semantics of the language, including object, function, boolean, symbol, and various error objects, objects that represent and manip numeric values including math, number, and 8, the text processing objects string and regexp, objects that are indexed collections of values including array and 9 different kinds of typed arrays whose elements all have a specific numeric data representation, keyed collections including map and set objects, objects supporting structured data including the JSON object, array buffer, shared array buffer, and data view. Objects supporting control abstractions including generator functions and promise objects, and reflection objects including proxy and reflect. ECMA script also defines a set of built-in operators. ECMA script operators include various unary operations, multiplicative operators, additive operators, bitwise shift operators, relational operators, equality operators, binary bitwise operators, binary logical operators, assignment operators, and the comma operator. Large ECMA script programs are supported by modules which allow a program to be divided into multiple sequences of statements and declarations. Each module explicitly identifies declarations it uses that need to be provided by other modules and which of its declarations are available for use by other modules. ECMA symbols Java syntax. ECMA script syntax is relaxed to enable it to serve as an easy-to-use scripting language. For example, a variable is not required to have its type declared nor a types associated with.
I wonder if chatbot questions if I'm writing an operating system because I'm good at assembly. YouTube doesn't have to like recommend my videos or promote them or whatever. It's not gonna stop what's coming though.
In various ways including via.
So I don't know. I'm gonna like check the output, make sure it looks correct and stuff. Because if it's fast or whatever, it doesn't mean anything if it doesn't work. So I don't know. I'm gonna need a minute to like type this up and freaking test it. Uno momento.
Invoke copyright sign.
I wonder if I could like just make macros instead.
Example, date, produces a string representation of the current date and time rather than an object. Every object created by a constructor has an implicit ref.
That's a bit more work. Never mind. I'm gonna actually type it up and run it to make sure it's actually counting the bit, the highest bit set.
And so on.
So, I'll talk again a bit. I gotta like find some music to listen to and then freaking this will take a minute to output this.
First
but then, I don't know. If it doesn't work, I'll tweak it until it's working.
The reference refers.
And it should still be faster.
Named property. The prototype.
Or not. Guess I'll find out.
Figure 1. Object Prototype Relationships CF Prototype P1 P2 Implicit Prototype Link Explicit Prototype Property CFP CFP1 CF1 Q1 Q2 CF2 Q1 Q2 CF3 Q1 Q2 CF4 Q1 Q2 CF5 Q1 Q2. In a class-based object-oriented language, in general, state is carried by instances, methods are carried by classes, and inheritance is only of structure and behavior. In ECMA script, the state and methods are carried by objects, while structure, behavior, and state are all inherited, or objects that do not directly contain a particular property that their prototype contains share that property and its value. Figure 1 illustrates this. CF is a constructor and also an object. 5 objects have been created by using new expressions: CF1, CF2, CF3, CF4, and CF5. Each of these objects contains properties named Q1 and Q2. The dashed lines represent the implicit prototype relationship. So, for example, CF3's prototype is CFP. The constructor, CF, has 2 properties itself, named P1 and P2, which are not visible to CFP, CF1, CF2, CF3, CF4, or CF5. The property named CFP1 in CFP is shared by CF1, CF2, CF3, CF4, and CF5, but not by CF, as are any properties found in CFP's implicit prototype chain that are not named Q1, Q2, or CFP1. Notice that there is no implicit prototype link between CF and CFP. Unlike most class-based object languages, properties can be added to objects dynamically by assigning values to them. That is, constructors are not required to name or assign values to all or any of the constructed object's properties. In the above diagram, one could add a new shared property for CF1, CF2, CF3, CF4, and CF5 by assigning a new value to the property in CFP. Although ECMA script objects are not inherently class-based, it is often convenient to define class-like abstractions based upon a common pattern of constructor functions, prototype objects, and methods. The ECMA script built-in objects themselves follow such a class-like pattern. Beginning with ECMA script 2015, the ECMA script language includes syntactic class definitions that permit programmers to concisely define objects that conform to the same class-like abstraction pattern used by the built-in objects. ECMA International 2024 5.4.3 to the strict variant of ECMA script. The ECMA script language recognizes the possibility that some users of the language may wish to restrict their usage of some features available in the language. They might do so in the interests of security, to avoid what they consider to be error-prone features, to get enhanced error checking, or for other reasons of their choosing. In support of this possibility, ECMA script defines a strict variant of the language. The strict variant of the language excludes some specific syntactic and semantic features of the regular ECMA script language and modifies the detailed semantics of some features. The strict variant also specifies additional error conditions that must be reported by throwing error exceptions in situations that are not specified as errors by the non-strict form of the language. The strict variant of ECMA script is commonly referred to as the strict mode of the language. Strict mode selection and use of the strict mode syntax and semantics of ECMA script is explicitly made at the level of individual ECMA script source text units as described in 1.1.2.2. Because strict mode is selected at the level of a syntactic source text unit, strict mode only imposes restrictions that have local effect within such a source text unit. Strict mode does not restrict or modify any aspect of the ECMA script semantics that must operate consistently across multiple source text units. A complete ECMA script program may be composed of both strict mode and non-strict mode ECMA script source text units. In this case, strict mode only applies when actually executing code that is defined within a strict mode source text unit. In order to conform to this specification, Any CMA script implementation must implement both the full unrestricted ECMA script language and the strict variant of the ECMA script languages defined by the specification. In addition, an implementation must support the combination of unrestricted and strict mode source text units into a single composite program. Point 4 Terms and definitions. For the purposes of this document, the following terms and definitions apply. 4.1 Implementation approximated. An implementation approximated facility is defined in whole or in part by an external source but has a recommended ideal behavior in this specification. 4.2 Implementation defined. An implementation defined facility is defined in whole or in part by an external source to this specification. 4.3 Host defined. Same as implementation defined. Note editorially. See clause 4.2, 4.4 Type. Set of data values as defined in clause 6.4. 5 Primitive value. Member of one of the types undefined. Null, boolean, number, big int, symbol, or string as defined in clause 6. Note a primitive value is a datum that is represented directly at the lowest level of the language implementation. Copyright sign, ECMA International 2024. 4.6 Object. Member of the type object. Note an object is a collection of properties and has a single prototype object. The prototype may be null. 4.7 Constructor. Function object that creates and initializes objects. 4.8 Prototype. Object that provides shared properties for other objects. 4.9 Ordinary object. Object that has the default behavior for the essential internal methods that must be supported by all objects. 4.10 Exotic object. Object that does not have the default behavior for one or more of the essential internal methods. Note any object that is not an ordinary object is an exotic object. The 4th of April 2011 standard object. Object whose semantics are defined by the specification. 4.12 Built-in object. Object specified and supplied by an ECMA script implementation. 4.13 Undefined value. Primitive value used when a variable has not been assigned a value. Note the value of a constructor's prototype property is a prototype object that is used to implement inheritance and shared properties. Note when a constructor creates an object, that object implicitly references the constructor's prototype property for the purpose of resolving property references. The constructor's prototype property can be referenced by the program expression constructor prototype, and properties added to an object's prototype are shared, through inheritance, by all objects sharing the prototype. Alternatively, a new object may be created with an explicitly specified prototype by using the object create built-in function. Note standard built-in objects are defined in this specification. Any CMA script implementation may specify and supply additional kinds of built-in objects. ECMA International 2024-7. The 4th of April 2014 Undefined type. Type whose sole value is the undefined value. 4.15 Null value. Primitive value that represents the intentional absence of any object value. 4.16 Null type. Type whose sole value is the null value. 4.17 Boolean value. Member of the Boolean type. Note there are only two Boolean values, true and false. 4.18 Boolean type. Type consisting of the primitive values true and false. The 4th of April 2019 Boolean object. Member of the object type that is an instance of the standard built-in Boolean constructor. 4.20 String value. Primitive value that is a finite ordered sequence of 0 or more 16-bit unsigned integer values. 4.21 String type. Set of all possible string values. 4.22 String object. Member of the object type that is an instance of the standard built-in string constructor. A Boolean object is created by using the Boolean constructor in a new expression, supplying the note Boolean value as an argument. The resulting object has an internal slot whose value is the Boolean value. A Boolean object can be coerced to a Boolean value. Note a string value is a member of the string type. Each integer value in the sequence usually represents a single 16-bit unit of UTF-16 text. However, ECMA script does not place any restrictions or requirements on the values except that they must be 16-bit unsigned integers. A string object is created by using the string constructor in a new expression, supplying a string note value as an argument. The resulting object has an internal slot whose value is the string value. Capital A, string object can be coerced to a string value by calling the string constructor as a function. 221111. Copyright sign, ECMA International 2024. The 4th of April 2023 number value. Primitive value corresponding to a double precision 64-bit binary format, i.e. E7542019. Value. Note: a number value is a member of the number type and is a direct representation of a number. 4.24 number type. Set of all possible number values including the special not a number. Nan. Value. Positive infinity and negative infinity. 4.25 number object. Member of the object type that is an instance of the standard built-in number constructor. 4.26 infinity. Number value that is the positive infinite number value. 4.27 nan. Number value that is an i.e. EE7542019. Not a number value. The 4th of April 2028 begint value. Primitive value corresponding to an arbitrary precision integer value. The 4th of April 2029 begint type. Set of all possible begint values. 4.30 begint object. Member of the object type that is an instance of the standard built-in begint constructor. The 4th of April 1931 symbol value. Primitive value that represents a unique non-string object property key. The 4th of April 1932 symbol type. Set of all possible symbol values. 4.33 symbol object. Member of the object type that is an instance of the standard built-in symbol constructor. A number object is created by using the number constructor in a new expression, supplying a note number value as an argument. The resulting object has an internal slot whose value is the number value. A number object can be coerced to a number value by calling the number constructor as a function. 211111. ECMA International 2024 9. The 4th of April 1934 function. Member of the object type that may be invoked as a subroutine. 4.35 built-in function. Built-in object that is a function. 4.36 built-in constructor. Built-in function that is a constructor. 4.37 property. Part of an object that associates a key, either a string value or a symbol value, and a value. 4.38 method. Function that is the value of a property. 4.39 built-in method. Method that is a built-in function. 4.40 attribute. Internal value that defines some characteristic of a property. 4.41 own property. Property that is directly contained by its object. Note: in addition to its properties, a function contains executable code and state that determine how it behaves when invoked. A function's code may or may not be written in ECMA script. Examples of built-in functions include parse, int, and math.exp. A host or implementation may, note, provide additional built-in functions that are not described in this specification. Examples of built-in constructors include object and function. A host or implementation may, note, provide additional built-in constructors that are not described in this specification. Note: depending upon the form of the property, the value may be represented either directly as a data value, a primitive value, an object, or a function object, or indirectly by a pair of accessor functions. Note: when a function is called as a method of an object, the object is passed to the function as its this value. Note: standard built-in methods are defined in this specification. A host or implementation may provide additional built-in methods that are not described in this specification. 0. Copyright sign, ECMA International 2024. The 4th of April 1942 inherited property. Property of an object that is not a known property but is a property either owned or inherited of the object's prototype. Point 5. Organization of this specification. The remainder of this specification is organized as follows. Clause 5 defines the notational conventions used throughout the specification. Clauses 6 through 10 define the execution environment within which ECMA script programs operate. Clauses 11 through 17 define the actual ECMA script programming language, including its syntactic encoding and the execution semantics of all language features. Clauses 18 through 28 define the ECMA script standard library. They include the definitions of all of the standard objects that are available for use by ECMA script programs as they execute. Clause 29 describes the memory consistency model of accesses on shared array buffer back memory and methods of the atomics object. Notational conventions. Point 1. Syntactic and lexical grammars. 5. 1. 1. Context-free grammars. A context-free grammar consists of a number of productions. Each production has an abstract symbol called a non-terminal as its left-hand side, and a sequence of 0 or more non-terminal and terminal symbols as its right-hand side. For each grammar, the terminal symbols are drawn from a specified alphabet. A chain production is a production that has exactly one non-terminal symbol on its right-hand side along with 0 or more terminal symbols, starting from a sentence consisting of a single distinguished non-terminal, called the goal symbol. A given context-free grammar specifies a language, namely, the, perhaps infinite, set of possible sequences of terminal symbols that can result from repeatedly replacing any non-terminal in the sequence with the right-hand side of a production for which the non-terminal is the left-hand side. 1.2 The lexical and regexp grammars. A lexical grammar for ECMA script is given in clause 12. This grammar has as its terminal symbols Unicode code points that conform to the rules for source character defined in 11.1. It defines a set of productions, starting from the goal symbol input element div, input element template tail, input element regexp, capital I, N, P, U, T, capital E, L, E, M, E, N, T, capital R, E, G, capital E, X, P, capital O, R, capital T, E, M, P, L, A, T, E, capital T, A, or input element #bang or regexp, that describe how sequences of such code points are translated into a sequence of input elements. Input elements other than white space and comments form the terminal symbols for the syntactic grammar for ECMA script and are called ECMA script tokens. These tokens are the reserved words, identifiers, literals, and punctuators of the ECMA script language. Moreover, line terminators, although not considered to be tokens, also become part of the stream of input elements and guide the process of automatic semicolon insertion. 12.10. Simple white space and single line comments are discarded and do not appear in the stream of input elements for the syntactic grammar. A multi-line comment, that is, a comment of the form comma regardless of whether it spans more than one line, is likewise simply discarded if it contains no line terminator, but if a multi-line comment contains one or more line terminators, then it is replaced by a single line terminator, which becomes part of the stream of input elements for the syntactic grammar. ECMA International 2024-11. A regexp grammar for ECMA script is given in 2.2.2.1. This grammar also has as its terminal symbols the code points as defined by source character. It defines a set of productions, starting from the goal symbol pattern, that describe how sequences of code points are translated into regular expression patterns. Productions of the lexical and regexp grammars are distinguished by having two colons, as separating punctuation. The lexical and regexp grammars share some productions. 1.3 The numeric string grammar. A numeric string grammar appears in 7.1.4.1. It has as its terminal symbols source character, and is used for translating strings into numeric values starting from the goal symbol string numeric literal, which is similar to but distinct from the lexical grammar for numeric literals. Productions of the numeric string grammar are distinguished by having three colons, as punctuation, and are never used for parsing source text. 1.4 The syntactic grammar. The syntactic grammar for ECMA script is given in clauses 13 through 16. This grammar has ECMA script tokens defined by the lexical grammar as its terminal symbols. 5.1.2. It defines a set of productions, starting from two alternative goal symbols script and module, that describe how sequences of tokens form syntactically correct independent components of ECMA script programs. When a stream of code points is to be parsed as an ECMA script or module, it is first converted to a stream of input elements by repeated application of the lexical grammar. This stream of input elements is then parsed by a single application of the syntactic grammar. The input stream is syntactically in error if the tokens in the stream of input elements cannot be parsed as a single instance of the goal non-terminal, script or module, with no tokens left over. When a parse is successful, it constructs a parse tree. A rooted tree structure in which each node is a parse node. Each parse node is an instance of a symbol in the grammar. It represents a span of the source text that can be derived from that symbol. The root node of the parse tree, representing the whole of the source text, is an instance of the parser's goal symbol. When a parse node is an instance of a non-terminal, it is also an instance of some production that has that non-terminal as its left-hand side. Moreover, it has 0 or more children, one for each symbol on the production's right-hand side. Each child is a parse node that is an instance of the corresponding symbol. New parse nodes are instantiated for each invocation of the parser and never reused between parsers even of identical source text. Parse nodes are considered the same parse node if and only if they represent the same span of source text, are instances of the same grammar symbol, and resulted from the same parser invocation. Note 1. Parsing the same string multiple times will lead to different parse nodes. For example, consider let str equals 1 plus 1 eval, str eval, str. Each call to eval converts the value of str into ECMA script source text and performs an independent parse that creates its own separate tree of parse nodes. The trees are distinct even though each parse operates upon a source text that was derived from the same string value. Note 2. Parse nodes are specification artifacts, and implementations are not required to use an analogous data structure. Productions of the syntactic grammar are distinguished head by having just one colon as punctuation. 2. Copyright sign, ECMA International 2024. The syntactic grammar as presented in clauses 13 through 16 is not a complete account of which token sequences are accepted as a correct ECMA script or module. Certain additional token sequences are also accepted, namely, those that would be described by the grammar if only semicolons were added to the sequence in certain places, such as before line terminator characters. Furthermore, certain token sequences that are described by the grammar are not considered acceptable if a line terminator character appears in certain awkward places. In certain cases, in order to avoid ambiguities, the syntactic grammar uses generalized productions that permit token sequences that do not form a valid ECMA script or module. For example, this technique is used for object literals and object destructuring patterns. In such cases, a more restrictive supplemental grammar is provided that further restricts the acceptable token sequences. Typically, an early error rule will then state that, in certain contexts, P must cover an N, where P is a parse node, an instance of the generalized production, and N is a non-terminal from the supplemental grammar. This means the sequence of tokens originally matched by P is parsed again using N as the goal symbol. If N takes grammatical parameters, then they are set to the same values used when P was originally parsed. If the sequence of tokens can be parsed as a single instance of N, with no tokens left over, then we refer to that instance of N, a parse node, unique for a given P, as the N that is covered by P. All early error rules for N and its derived productions also apply to the N that is covered by P. Otherwise, if the parse fails, it is an early syntax error. 1.5 Grammar notation 5. 1. 5. 1 Terminal symbols. In the ECMA script grammars, some terminal symbols are shown in fixed-width font. These are to appear in a source text exactly as written. All terminal symbol code points specified in this way are to be understood as the appropriate Unicode code points from the basic Latin block, as opposed to any similar-looking code points from other Unicode ranges. A code point in a terminal symbol cannot be expressed by a Unicode escape sequence in grammars whose terminal symbols are individual Unicode code points, that is, the lexical, regexp, and numeric string grammars, a contiguous run of multiple fixed-width code points appearing in a production is a simple shorthand for the same sequence of code points, written as standalone terminal symbols. For example, the production hex integer literal 0x hex digits is a shorthand for hex integer literal 0x hex digits. In contrast, in the syntactic grammar, a contiguous run of fixed-width code points is a single terminal symbol. Terminal symbols come in two other forms. In the lexical and regexp grammars, Unicode code points without a conventional printed representation are instead shown in the form ABBREV, where ABBREV is an mnemonic for the code point or set of code points. These forms are defined in Unicode format control characters, white space, and line terminators. In the syntactic grammar, certain terminal symbols, for example identifier name and regular expression literal, are shown in italics, as they refer to the non-terminals of the same name in the lexical grammar. ECMA International 2024-13. 5. 1. 5. 2 non-terminal symbols and productions. Non-terminal symbols are shown in italic type. The definition of a non-terminal, also called a production, is introduced by the name of the non-terminal being defined followed by one or more colons. The number of colons indicates to which grammar the production belongs. One or more alternative right-hand sides for the non-terminal then follow on succeeding lines. For example, the syntactic definition while statement while expression statement states that the non-terminal while statement represents the token while, followed by a left parenthesis token, followed by an expression, followed by a right parenthesis token, followed by a statement. The occurrences of expression and statement are themselves non-terminals. As another example, the syntactic definition argument list, assignment expression, argument list, assignment expression, states that an argument list may represent either a single assignment expression or an argument list, followed by a comma, followed by an assignment expression. This definition of argument list is recursive, that is, it is defined in terms of itself. The result is that an argument list may contain any positive number of arguments, separated by commas, where each argument expression is an assignment expression. Such recursive definitions of non-terminals are common. 1, 5, 3 optional symbols. The subscripted suffix opt, which may appear after a terminal or non-terminal, indicates an optional symbol. The alternative containing the optional symbol actually specifies 2 right-hand sides, one that omits the optional element and one that includes it. This means that variable declaration binding identifier initializer opt is a convenient abbreviation for variable declaration binding identifier initializer, and that for statement 4 lexical declaration is a convenient abbreviation for statement 4 lexical declaration 4 lexical declaration, which in turn is an abbreviation for expression statement, expression statement, expression statement, expression statement. 4. ECMA International 2024 for statement 4 lexical declaration. So, in this example, the non-terminal for statement actually has 4 alternative right-hand sides. 5. 1. 5. For grammatical parameters, a production may be parameterized by a subscripted annotation of the form parameters, which may appear as a suffix to the non-terminal symbol defined by the production. Parameters may be either a single name or a comma-separated list of names. A parameterized production is shorthand for a set of productions defining all combinations of the parameter names, preceded by an underscore, appended to the parameterized non-terminal symbol. This means that statement list, return statement, expression statement is a convenient abbreviation for statement list, return statement, expression statement, statement list return statement, expression statement, and that statement list, return statement, expression statement is an abbreviation for statement list, return statement, expression statement, statement list return statement, expression statement, statement list in, return statement, expression statement, statement list return in, return statement, expression statement. Multiple parameters produce a combinatory number of productions, not all of which are necessarily referenced in a complete grammar. References to non-terminals on the right-hand side of a production can also be parameterized. For example, statement list, return statement, expression statement, plus in ECMA International 2024 5.
I don't know. And it sucked. Stupid fan is on.
Expression statement in is equivalent to statement list, return statement, expression statement. A non-terminal reference may have both a parameter list and an opt suffix. For example, variable declaration, binding identifier initializer, plus inopt is an abbreviation for
It would suck to lose the game.
binding.
Luckily, I never lose.
Fixing a parameter name with on a right-hand side non-terminal reference makes that parameter value dependent upon the occurrence of the parameter name on the reference to the current production's left-hand side symbol. For example, variable declaration in binding identifier initializer in is an abbreviation for variable declaration, binding identifier initializer, variable declaration in, binding identifier initializer in. If a right-hand side alternative is prefixed with plus parameter, that alternative is only available if the named parameter was used in referencing the production's non-terminal symbol. If a right-hand side alternative is prefixed with parameter, that alternative is only available if the named parameter was not used in referencing the production's non-terminal symbol. This means that statement list, return plus return statement, expression statement is an abbreviation for statement list, expression statement. 6. ECMA International 2024. Statement list, return statement, statement list return statement, expression statement, and that statement list, return statement, expression statement is an abbreviation for statement list, return statement, express iron statement, statement list return, expression statement, 1, 5, 5 1 of. When the words 1 of follow the colon, s, in a grammar definition, they signify that each of the terminal symbols on the following line or lines is an alternative definition. For example, the lexical grammar-free CMA script contains the production, non-zero digit, 1 of 123,456,789, which is merely a convenient abbreviation for non-zero digit. 1, 3, 4, 5, 6, 7, 8, 9, 1, 5, 6, empty. If the phrase empty appears as the right-hand side of a production, it indicates that the production's right-hand side contains no terminals or non-terminals. 1, 5, 7 look ahead restrictions. If the phrase look ahead equals sec appears in the right-hand side of a production, it indicates that the production may only be.
This is taking way too long to just test the result.
At, where set is a finite,
I gotta
indicates that the production may only be used if some element of set is a prefix of the immediate.
I don't know, I'm gonna try this first.
For convenience, the set.
I have a loop below. Need some water. That loops through an array, converts it to hexadecimal, and prints it, or outputs it to the string that goes to the window.
Indicate
And I just lazily
used if sec is not
copied the part that computes it,
and
then passing in the value to print,
element of set is a prefix of the immediate.
which is RSP, and this one's gonna be out of range.
7, 8, 9 decimal digits. Decimal digit.
They're actually all out of range
The definition. Look ahead example. N
because I need to be passing in
5, 7, 9 decimal digits. Decimal digit. Look ahead decimal digit matches either the letter N followed by one or more decimal digits, the first of which is even, or a decimal digit not followed by another decimal digit. Note that when these phrases are used in the syntactic grammar, it may not be possible to unambiguously ident.
Okay, so this is from the loop where it computes the offset to get the value from. So I need to be using this to set the value to instead.
It is considered an editorial error for a token sequence sec to appear in a look ahead restriction
So if I set
part of a set of sequences, if the choices of lexical
AX to SP,
would be a prefix of
hold the result.
1, 5, 8, no line terminator here. If the phrase no line
I need to be passing in
side of a production of the
the indice to set it to. That goes here.
production, it may not be used if a line as in the input S stream at the indicator
And I need to pass in the value to set.
statement. Throw, no line terminator here. Expression indicates that the production may not be used if a line terminator occurs in the script between
So I'll use
unless the
SP to pass in the value to set.
number of occurrences
Because nothing else using SP.
appear between any two consecutive tokens in the stream of tick acceptability of the script, comma 1.
Otherwise I gotta like rewrite part of this.
Right-hand side of a production may specify that
I'll just replace this part.
using the phrase but not
Just pass in REX.
extensions to be excluded. For example, the production identifier name but not reserved word means that the non-terminal identifier may be replaced by any sequence of code points that could replace identifier name provided that the same sequence of code points could not replace reserved word.
But I can't. Because multiply uses REX.
510 descriptive phrase. Non-terminal symbols are described by a descriptive phrase.
So I'll move the value to RCX.
Source character, any Unicode code. Algorithm conventions. The specification often uses a numbered list to specify steps in an algorithm. These algorithms are used to precisely
So I'll
specify
move REX to RCX.
a script language constructs
Make sure it's not being used.
intended to imply the use of any specific implementation.
And then after here,
There may be more efficient algorithms available to implement a given feature.
RCX holds value.
Parameter,
So
comma-separated sequence of
just do RDI.
used within the algorithm steps to reference the argument part.
Put on the double check.
Optional parameters are denoted with surrounding brackets. Name, and no different from required parameters within algorithm steps. A rest parameter may appear at the end of a parameter list, denoted with leading ellipsis. Name. The rest parameter captures all of the arguments provided following the required and optional parameters into a list. If there are no such additional arguments, that list is empty. Algorithm steps may be subdivided into sequential substeps. Substeps are indented and may themselves be further divided into indented substeps. Outline numbering conventions are used to identify substeps, with the first level of substeps labeled with lowercase alphabetic characters and the second level of substeps labeled with lowercase Roman numerals. If more than 3 levels are required, these rules repeat with the 4th level using numeric labels. For example, top level step A substep B substep, I substep, substep, a substep, I substep. A step or substep may be written as an if predicate that conditions its substeps. In this case, the substep
This is taking way longer than I thought it would.
begins with the word L,
So I got RCX.
preceding if predicate step at the same level. A step may specify the iterative application of its substeps. A step that begins with assert asserts an invariant condition of its algorithm. Such assertions are used to make explicit algorithmic invariant.
Zero out RCX after.
Such assertions add no additional semantic requirements and hence need not be checked by implementation. They are used simply to clarify algorithms. Algorithm step
This is a mess of just reusing code all over the place.
both X and sym.
But it'll work for now. Alright. Almost done.
Avoid this reference-like behavior should explicitly make a copy of
Hopefully this will work on first try.
some value creates a shallow copy of some value. Once declared, an alias may be referenced in any subsequent steps and must not be referenced from steps prior to the alias.
Why is it doing this?
May be modified using the form set X to some other value, 2.1 abstract operations. In order to facilitate that using multiple parts of this specification, some algorithms, called abstract operations, are named and written in parameterized functional form so that they may be referenced by name from within other algorithms. Abstract operations are typically referenced using a functional application style such
Why is it not syntax colored?
arg1, arg2. Some abstract operations are treated as polymorphically dispatched methods of class-like specification abstract.
Sublime sucks.
Such method-like abstract operations are typically referenced using a method application style such as SymValue operation name, arg1, arg2, 2.2 syntax-directed operations. A syntax-directed operation is a named operation whose definition consists of algorithms, each of which is associated with one or more productions from one of the ECMA script grammars. A production that has multiple alternative definitions will typically have a distinct algorithm for each alternative. When an algorithm is associated with a grammar production, it may reference the terminal and non-terminal symbols of the production alternative as if they were parameters of the algorithm. When used in this manner, non-terminal symbols refer to the actual alternative definition that is matched when parsing the source text. The source text matched by a grammar production or parse node derived from it is the portion of the source text that starts at the beginning of the first terminal that participated in the match and ends at the end of the last terminal that participated in the match. When an algorithm is associated with a production alternative, the alternative is typically shown without any grammar annotations. Such annotations should only affect the syntactic recognition of the alternative and have no effect on the associated semantics for the alternative. Syntax-directed operations are invoked with a parse node and, optionally, other parameters by using the conventions on steps 1, 3, and 4 in the following algorithm. Let status be syntax-directed operation of some non-terminal. Let some parse node be the parse of some source text. Perform syntax-directed operation of some parse node. Perform syntax-directed operation of some parse node with argument value. Unless explicitly specified otherwise, all chain productions have an implicit definition for every operation that might be applied to that production's left-hand side non-terminal. The implicit definition simply reapplies the same operation with the same parameters, if any, to the chain production's sole right-hand side non-terminal and then returns the result. For example, assume that some algorithm has a step of the form, return evaluation of block and that there is a production block statement list, but the evaluation operation does not associate an algorithm with that production. In that case, the evaluation operation implicitly includes an association of the form, runtime semantics, evaluation block, statement list, return evaluation of statement list 5, 2, 3 runtime semantics. Algorithms which specify semantics that must be called at runtime are called runtime semantics. Runtime semantics are defined by abstract operations or syntax-directed operations. 2, 3, 1 completion record. The abstract operation completion takes argument completion record, a completion record, and returns a completion record. It is used to emphasize that a completion record is being returned. It performs the following steps when called. 2. Assert. Completion record is a completion record. Return completion record. 0. ECMA International 2024. 5. 2. 3. To throw an exception. Algorithm steps that say to throw an exception, such as 1. Throw a type error exception, mean the same things as return, throw completion, a newly created.
Now I just gotta turn off where it's overriding dailies right now.
1. Return.
This lazy jump table. It's not even a jump table. It's a bunch of conditional checks. Let me see.
Else. Set argument to argument. Algorithm steps that say or are otherwise equivalent to 1. Return of abrupt. Abstract operation mean the same thing as let hygienic temp be abstract operation. Assert. Hygienic temp is a completion record. If hygienic temp is an abrupt completion, return completion. Hygienic temp else. Set hygienic temp to hygienic temp, where hygienic temp is ephemeral and visible only in the steps pertaining to return if abrupt. Algorithm steps that say or are otherwise equivalent to let result be abstract operation. Return if abrupt. Argument mean the same thing as assert. Argument is a completion record. If argument is an abrupt completion, return completion. Argument else. Set argument to argument. Let result be abstract operation. Argument, 2, 3, 4 return of abrupt shorthands, invocations of abstract operations and syntax-directed operations that are
And the macro.
to the resulting completion record. For example, the step ? Operation name is equivalent.
Okay, there's a build though. Let's find out.
Name. Similarly, for method application style, the step $some value operation name ECMA International 2024-21 is equivalent to return of abrupt some value operation name. Similarly, prefix is used to indicate that the following
Nope. That's a build.
operation will never return an abrupt completion and that the resulting completion records field should be used in place of the return value of the operation. For example, the step let val be operation
I think it's stuck.
steps let val be operation name assert val is a normal completion set val to val syntax directed operations for runtime semantic
Another memory. It went out of bounds.
before the invocation
And then closed it.
form syntax directed
Now I'm gonna write to like 15 known addresses. And I'll just set them in that lazy jump table that I have.
to return a completion record, and within all built-in functions, the returned value is first passed to normal completion, and the result is used instead. This rule does not apply within the completion algorithm or when the value being returned is clearly marked as a completion record in that step. These cases are when the result of applying completion, normal completion, or throw completion is directly returned. When the result of constructing a completion record is directly returned, it is an editorial error if a completion record is returned from such an abstract operation through any other means. For example, within these abstract operations, return true means the same things as any of return normal completion, true, or let completion be normal completion, true, return completion, completion, or return completion record, normal, true, empty. Note that, through the return of abrupt expansion, the following example is allowed, as within the expanded steps. The result of applying completion is returned directly in the abrupt case and the implicit normal completion application occurs after unwrapping in the normal case. Return completion. The following example would be an editorial error because a completion record is being returned without being annotated in that step. 2. Let completion be normal completion. True. Return completion. 2. ECMA International 2024. 5. 2. 4. Static semantics. Context-free grammars are not sufficiently powerful to express all the rules that define whether a stream of
Okay, so now
script or module that may be evaluated
make 15 pairs above. Set them, and then set them down below.
them conventions or
Using a jump. To be super easy.
with the production of a grammar and are called the static semantics of the production. Static semantic rules have names and typically are defined using an algorithm. Named static semantic rules are associated with grammar productions, and a production that has multiple alternative definitions will typically have for each alternative a distinct algorithm for each applicable named static semantic rule. A special kind of static semantic rule is an early error rule. Early error rules define early error conditions, see clause 17, that are associated with specific grammar productions. Evaluation of most early error rules are not explicitly invoked within the algorithms of this specification. A conforming implementation must, prior to the first evaluation of a script or module, validate all of the early error rules of the productions used to parse that script or module. If any of the early error rules are violated, the script or module is invalid and cannot be evaluated. 2.5 Mathematical operations. This specification makes reference to these kinds of numeric values. Mathematical values. Arbitrary real numbers. Used as the default numeric type. Extended mathematical values. Mathematical values together with plus and numbers, i.e. 754, 2019. Double precision floating point values. Big ints. ECMA script language values representing arbitrary integers in a one-to-one correspondence. In the language of this specification, numerical values are distinguished among different numeric kinds using subscript suffixes. The subscript refers to numbers, and the subscript Z refers to big ints. Numeric values without a subscript suffix refer to mathematical values. Numeric operators such as plus, equals, and refer to those operations as determined by the type of the operands. When applied to mathematical values, the operators refer to the usual mathematical operations. When applied to extended mathematical values, The operators refer to the usual mathematical operations over the extended real numbers. Indeterminate forms are not defined and their use in this specification should be considered an editorial error. When applied to numbers, the operators refer to the relevant operations within IEEE 754-2019. When applied to big ints, the operators refer to the usual mathematical operations applied to the mathematical value of the big int. In general, when this specification refers to a numerical value, such as in the phrase, the length of y or the integer represented by the 4 hexadecimal digits, without explicitly specifying a numeric kind, the phrase refers to a mathematical value. Phrases which refer to a number or a big int value are explicit, y annotated as such. For example, the number value for the number of code points in, or the big int value for, numeric operators applied to mixed-type operands, such as a number and a mathematical value, are not defined and should be considered an editorial error in this specification. This specification denotes most numeric values in base 10. It also uses numeric values of the form 0x followed by digits 09 or AF as base 16 values. When the term integer is used in this specification, it refers to a mathematical value which is in the set of integers, unless otherwise stated. When the term integral number is used in this specification, it refers to a number value whose mathematical value is in the set of integers. Conversions between mathematical values and numbers or big ints are always explicit in this document. A conversion from a mathematical value or extended mathematical value x to a number is denoted as the number value for x or x, and is defined in 6.1.6.1. A conversion from an integer x to a big int is denoted as the big int value for x or z, x. A conversion from a number or big int x to a mathematical value is denoted as the mathematical value of x, or r, x. The mathematical value of +0 and -0 is the mathematical value 0. The mathematical value of non-finite values is not defined. The extended mathematical value of x is the mathematical value of x for finite values, and is plus and, for plus and, respectively. It is not defined for NaN, ECMA International 2024-23. The mathematical function abs, x, produces the absolute value of x, which is x of x, 0 and otherwise is x itself. The mathematical function min, x1, x2, xn, produces the mathematically smallest of x1 through xn. The mathematical function max, x1, x2, xn, produces the mathematically largest of x1 through xn. The domain and range of these mathematical functions are the extended mathematical values. The notation x modulo y must be finite and non-zero, computes a value k of the same sign as y, or 0, such that abs, k, abs, y, and x, k equals qy for some integer q. The
Taking quite a bit longer than I thought it would.
that lower upper produces lower if x,
This, it's not C language.
upper, and otherwise produces x. The mathematical function
It's, more technical.
produces the largest integer, closest to plus, that is not larger than x. Note floor, x equals x, x modulo 1. The mathematical function truncate, x, removes the fractional part of x by rounding towards 0, produce
I'm gonna run it first. I gotta, like, paste each of these blocks to set the address.
mathematical functions min, max,
Oh, come on.
and truncate are not defined for numbers and big ints, and any usage of those methods that have non-mathematical value arguments would be an editorial error in this specification. An interval from lower bound A to upper bound B is a possibly infinite, possibly empty set of numeric values of the same numeric type. Each bound will be described as either
Put it in the wrong way.
both. There are 4 kinds of intervals, as follows. An interval from A, inclusive, to B, inclusive, also called an inclusive interval from A to B, includes all values x of the same numeric type such that A x b, and no others. An interval from A, inclusive, to B, exclusive, includes all values x of the same numeric type such that A x, b, and no others. An interval from A, exclusive, to B, inclusive, includes all values x of the same numeric type such that a, x b, and no others. An interval from a, exclusive, to b, exclusive, includes all values x of the same numeric type such that a, x, b, and no others. For example, the interval from 1, inclusive, to 2, exclusive, consists of all mathematical values between 1 and 2, including 1 and not including 2. For the purpose of defining intervals, -0, +0. So, for example, an inclusive interval with a lower bound of +0 includes +0 but not -0. Nan is never included in an interval. 2.6 value notation. In this specification, ECMA script language values are displayed in bold. Examples include null, true, or hello. These are distinguished from ECMA script source text such as function prototype apply or let n equals 42, 2.7 identity. In this specification, both specification values and ECMA script language values are compared for equality.
Almost done. Paste it for all these.
Values without identity are equal to other values without identity if all
Oh, this tastes stupid.
characteristics such as the magnitude of an integer or the length of a sequence. Values without identity may be manifest without prior reference by fully describing their characteristics. In contrast, each value with identity is unique and therefore only equal to itself. Values with identity are like values without identity but with an additional unguessable, unchangeable, universally unique characteristic called identity. References to existing values with identity cannot be manifest simply by describing them, as the identity itself is indescribable. Instead, references to these values must be explicitly passed from one place to another. Some values with identity are mutable and therefore can have their characteristics except their 24. Copyright sign, ECMA International 2024. Identity, changed in place, causing all holders of the value to observe the new characteristics. A value without identity is never equal to a value with identity. From the perspective of this specification, the word is used to compare two values for equality, as in if bool is true, then, and the word contains is used to search for a value inside lists using equality comparisons. As an if list contains a record R such that R. Sification, from the perspective of the ECMA script language. Language values are compared for equality using the same value abstract operation in the abstract operations it transitively calls. The algorithms of these comparison abstract operations determine language identity of ECMA script language values. For specification values, examples of values without specification identity include, but are not limited to, mathematical values and extended mathematical values, ECMA script source text, surrogate pairs, directive prologues, etc., UTF, 16 code units, Unicode code points, enums,
Is mic working? I hate this streaming software.
with specification identity include, but are not limited,
Alright, I'm in test works.
including property descriptors, private elements, etc., parse nodes, lists, sets and relations, abstract closures, data blocks, private names, execution contexts and execution context stacks, agent signifiers, and waiter list records. Specification identity agrees with language identity for all ECMA script language values except symbol values produced by symbol 4. The ECMA script
Okay, it's outputting
identity and without
the correct number.
are undefined, null, booleans, strings, numbers, and bigins. The ECMA script language values with
But it's not running the routine. So now it's outputting the list. And it's jumping, everything's working. So now I just gotta put in the routine.
The possible value types are exactly those defined in this clause. Types are further subclassified into ECMA script language types and specification types. Within this specification, the notation type, X, is used as shorthand for the type of X, where type refers to the ECMA script language and specification types defined in this clause. Point 1. ECMA script language types. An ECMA script language type corresponds to values that are directly manipulated by an ECMA script program using the ECMA
Let's set them all to like
script language types are undefined, null, boolean, string,
0xFFF.
big int, and object.
Only the top half or something.
Value is a value that is characterized by an ECMA script language type, 1.1. The undefined type. The undefined type has exactly one value, called undefined. Any variable that has not been assigned a value has the value.
Just a double check.
2. The null type. The null type has exactly one value, called null 6, 1. 3. The Boolean type. The Boolean type represents a logical entity having two values, called true and false. ECMA International 2000.
Okay, so it works for sure.
1. For the string type. The string type is the set of all ordered sequences of 0
I'll pass in the routine.
values, elements, up to a maximum length of 253 elements. The string type is generally used to represent textual data in a running ECMA script program, in which case each element in the string is.
So I'm setting the register to 1, redshift 0, 1, redshift 1,
Occupying a position.
and so on.
These positions are indexed with non-negative integers.
And printing it to 0, 1, 2, 3, 4, whatever.
Any at index 1, and so on.
So just gotta put the routine right here.
Of elements. That is, 16-bit values.
Gotta double check. The SP passes it in, and RAX holds result.
CMA script operations that do not interpret string content supply no further semantics. Operations that do interpret
SP passes it in.
as a single UTF-16 code unit. However, ECMA script does not restrict the value of all relationships between these code units, so operations that further interpret string contents as sequences of Unicode code points encoded in UTF-16 must account for ill-formed subsequences. Such operations apply special treatment to every code unit with a numeric value in the inclusive interval from 0xD800 to 0xTBFF, defined by the Unicode.
It looks like Chaput's using CL to pass back the result. And then mine has DX. So,
or more formally as a low surrogate code unit, using the following rules. A code unit that
DX and CX.
not a trailing surrogate is interpreted as a code point with the same value. A sequence of two code units, where the first code unit C1 is a leading surrogate and the second code unit C2 a trailing surrogate, is a surrogate pair and is interpreted as a code point with the value C1 0xD800, 0 times 400 plus C2 0xDC00, plus 0 times 10,000, C1 1, 1, 3.
I also need to make it zero out all the registers. Ah, it's getting annoying.
Prototype normalize. C22, 1, 3, 1, 5 can be used to explicitly normalize a string value. String prototype locale compare. C22, 1, 3, 1, 2 internally normalizes string values, but no other operations implicitly normalize the strings upon which they operate. Operation results in not language and or locale sensitive unless stated otherwise. In this specification, the phrase the string concatenation of A, B, where each argument is a string value, a code unit, or a sequence of code units, denotes the string value whose sequence of code units is the concatenation of the code units. In order of each of the arguments. In order, the phrase the substring of S from inclusive start to exclusive end, where S is a string value or a sequence of code units and inclusive start and exclusive end are integers, denotes the string value consisting of the consecu type code units of S beginning at index inclusive start and ending immediately before index exclusive end, which is the empty string when inclusive start equals exclusive end. If the to suffix is omitted, the length of S is used as the value of exclusive end. The phrase the ASCII word characters denotes the following string value, which consists solely of every letter and number in the
Make I'll just make another macro that holds the zeroing out. You can never have too many macros until you run out macro expansion space. Then you have too many macros at that point.
String, search value, from index. The abstract operation string index of takes argument string, a string, search value, a string, and from index, a non-negative integer, and returns an integer. It performs the following steps when called. Let len be the length of string. If search value is the empty string and from index len, return from index. Let search len be the length of search value. Note the rationale behind this design was to keep the implementation of strings as simple and high-performing as possible. If ECMA script source text is in normalized form C, string literals are guaranteed to also be normalized, as long as they do not contain any Unicode escape sequences. 6. ECMA International 2024. 4. For each integer I such that from index I len, search len, in ascending order. Do a let candidate be the substring of string from I to I plus search len. B if candidate is search value, return I. Return -1. Note 2 this algorithm always returns -1 if from index plus the length of search value. The length of string, 1.5 the symbol type. The symbol type is the set of all non-string values that may be used as the key of an object property. 6. 1. 7. Each possible symbol value is unique and immutable. Each symbol value immutably holds an associated value called that is either undefined or a string value. 1. 5. 1 well-known symbols. Well-known symbols are built-in symbol values that are explicitly referenced by algorithms of this specification. They are typically used as the keys of properties whose values serve as extension points of a specification algorithm. Unless otherwise specified, well-known symbols values are shared by all.
Okay, so now it'll zero out the registers, and then I'll run the routine. In this macro that wraps the other macro, it'll move it to REX, RDX, or RCX based on the routine. That way, I don't have to rewrite this.
Code unit, specification name, description.
I just want the result, simply. I could put in the loop above, but then it gets complicated because I got to break from the loop and a whole bunch of other things because the loop's involved.
Method that determines if a
I think it's probably just as complicated as aligning it like I am right now.
by the
This probably isn't saving any time.
concat
This might be taking more time.
Boolean valued object should be flattened to its array elements by array prototype concat at iterator symbol iterator, a method that returns the default iterator for an object called by the semantics of the for of statement at match symbol match, a regular expression method that matches the regular expression against a string called by the string prototype match method. Copyright sign ECMA International 2024. 7. Table 1. Well-known symbols. Continued. Specification name. Description. Value and purpose. At match all. Symbol match all. A regular expression method that returns an iterator that yields matches of the regular expression against a string called by the string prototype match all method. At replace. Symbol replace. A regular expression method that replaces matched substrings of a string called by the string prototype replace method. At search. Symbol search. A regular expression method that returns the index within a string that matches the regular expression called by the string prototype search method. At species. Symbol species. A function valued property that is the constructor function that is used to create derived objects. At split. Symbol split. A regular expression method that splits a string at the indices that match the regular expression called by the string prototype split method. At to primitive. Symbol to primitive. A method that converts an object.
I think it's done. I think it'll work. So I'm gonna check chatbot first. Chatbot makes failed output. That way if mine doesn't work, I'll feel better about mine. Dang it.
type to string, at unscoppables, symbol, unscoppables, an object-valued property whose own and inherited property names are property names that are excluded from the with environment bindings of the associated object. 6. 1. ECMA script has two built-in numeric types, number and bigint. The following abstract operations are defined over these numeric types. The result column shows the return type, along with an indication of it is possible for some invocations of the operation to return an abrupt completion. Table 2. Numeric type operations. Operation. Example source. Invoked by the evaluation semantics of result. Number. Unary minus x. Unary. Operator. Number. Bigint. Unary minus bigint. Number. Bitwise not x. Bitwise not operator. Number. Bigint. Bitwise not bigint. Number. Exponentiate. XY. Exponentiation operator and mathpal. Base. Exponent. Number. 28. ECMA International 2024. Table 2. Numeric type operations. Continued. Operation. Example source. Invoked by the evaluation semantics of result. Bigint. Exponentiate. Either a normal completion containing a bigint or a throw completion. Number. Multiply. XY. Multiplicative operators. Number. Bigint. Multiply. Bigint. Number. Divide. XY. Multiplicative operators. Number. Bigint. Divide. Either a normal completion containing a bigint or a throw completion. Number. Remainder. X% Y. Multiplicative operators. Number. Bigint. Remainder. Either a normal completion containing a bigint or a throw completion. Number. Add. X plus 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 x x plus y. Postfix increment operator. Prefix increment operator. And the addition operator. Plus. Number. Bigint. Add. Bigint. Number. Subtract. X. X x y. Postfix decrement operator. Prefix decrement operator. Operator. Number. Bigint. Subtract. Bigint. Number. Left shift x. Y. The left shift operator. Number. Bigint. Left shift. Bigint. Number. Signed right shift x. Y. The signed right shift operator. Number. Bigint. Signed right shift. Bigint. Number. Unsigned right shift x. Y. The unsigned right shift operator. Number. Bigint. Unsigned right shift. A throw completion. Number. Less than.
X, y X, y X, igual a y X, igual a y.
Relational operators. Vi is less than. X. Y. Left first. Boolean or undefined. For unordered inputs. Bigint. Less than. Boolean. Number. Equal. X equals equals Y. X equals Y. X equals 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 Y. X equals Y. Equality operators. Vi is strictly equal. X. Y. Boolean. Bigint. Equal. Copyright sign. ECMA International 2024. 9. Table 2. Numeric type operations. Continue.
Why doesn't it build? Seriously?
Of result. Number. Same value. Object is X. Y. Object internal methods. Via same value. X. Y. To test exact value equality. Boolean. Number. Same value 0. X includes. Y. Array. Map. And set methods. Via same value 0. X. Y. To test value equality. Ignoring the difference between +0 and -0. Boolean. Number. Bitwise and X and Y. Binary bitwise operators. Number. Bigint. Bitwise and bigint. Number. Bitwise or XY. Number. Bigint. Bitwise or bigint.
What the fuck?
Y. Number. Bigint. Bitwise or bigint. Number. To string. String. X. Many expressions and built-in functions. Vi to string. Argument. String. Bigint. To string, because the numeric types are in general not convertible without loss of precision or truncation. The ECMA script language provides no implicit conversion among these types. Programmers must explicitly call number and bigint functions to convert among types when calling a function which requires another type, 1, 6, 1 the number type, arithmetic, except that the 9, 0, 0, 7, 199, 254, 740, 990, that is, 253 2, distinct not a number values of the IEE standard are represented in ECMA script as a single special NaN value. Note that the nan value is produced by the program expression nan. In some implementations, external code might be able to detect a difference between various not a number values, but such behavior is implementation defined. To ECMA script code, all nan values are indistinguishable from each other. There are two other special values, called positive infinity and negative infinity. For brevity, these values are also referred to for expository purposes by the symbols plus and, respectively. Note that these two infinite number values are produced by the program expressions plus infinity, or simply infinity and infinity. Note the first and subsequent additions of
How is this invalid if it built last time?
numeric conversions that could lose precision or truncate. These legacy implicit conversions are maintained for backward compatibility, but not provided for big int in order to minimize opportunity for programmer error, and to leave open the option of generalized value types in a future edition. Note the bit pattern that might be observed in an array buffer, C25.1, or a shared array buffer, C25.2. After a number value has been stored into it is not necessarily the same as the internal representation of that number value used.
Huh.
Copyright sign, ECMA International 2000.
Built all these other times.
Expository purposes by the symbols +0 and -0, respectively. Note that these two different zero number values are produced by the program expressions +0, or simply 0, and -0.
Well, this is getting really annoying.
736, 874, 454, 810, 622, that is, 264, 253, 2. Finite non-zero values are of two kinds, SM2, E, where S is 1 or -1, M is an integer in the interval from 252, inclusive, to 253, exclusive, and E is an integer in the inclusive interval from -1000.
So, I'm gonna undo whatever I did.
007, 199, 254, 700.
Because I don't need a broken file. I just have to back up. Just gonna paste back.
Having the form SM2E, where S is 1 or -1, M is an integer in the interval from 0, exclusive, to 252, exclusive, and E is -1074. Note that all the positive and negative integers whose magnitude is no greater than 253 are representable in the number type. The integer 0 has two representations in the number type, +0 and -0. A finite number has an odd significant if it is non-zero and the integer M used to express it, in one of the two forms shown above, is odd.
Right here. Save. Build again. Reassemble.
Number value for X where X represents an exact
What? What? How did it build? There's other times.
type, with -0 removed and
Wait. Does it still run?
presentable in the number type, namely
What?
253 2971. Two values of the set are equally close, then the one with an even significant is chosen.
Well, I don't get it. It built perfectly fine and it ran. And now it's not. Is shift right AL DL even a valid instruction?
X 0
Did chatbot give me broken code? And did this assembler
this procedure
not catch that was broken until now?
4201. The value for plus is plus, and the number value for is. Some ECMA script operators deal only with integers in specific ranges such as the inclusive interval from -231 to 231 1 or the inclusive interval from 0 to 216 1. These operators accept any value of the number type but first convert each such value to an integer value in the expected range. See the descriptions of the numeric conversion operations in 7.1,1.
This is 2945.
The abstract operation number, unary minus takes argument x, a number, and returns a number. It performs the
That's here.
if x is nan, return the result of negating x.
2051.
Magnitude but opposite sign. ECMA International 2024 31 6 1 6 1 2 number. Bitwise not x. The abstract operation number, bitwise not takes argument x, a number, and returns an integral number. It performs the following steps when called. Let old value be to
Oh, 2951.
value. The mathematical value of the result is exactly representable as a 32-bit 2's complement bit string, 1 6 1 3 number, exponentiate, base, exponent. The abstract operation number, exponentiate takes arguments base, a number, and exponent
2951.
returns an implementation approximated value representing the result of raising base to the exponent power. It performs the following steps when called. If exponent is nan, return nan. If exponent is either plus 0 or minus 0, return 1. If base is nan, return nan. If base is plus, then if exponent
2957.
plus, otherwise, return plus 0, 5. If base is, then if exponent plus 0, then if exponent is an odd integral number, return, otherwise, return plus b else. If exponent is an odd integral number, return minus 0. Otherwise, return plus 0. If base is plus 0, then if exponent plus 0, return plus.
So shift right AXDL, shift right AXDL. Are they all AXDL? Yes.
b else. If exponent is an odd integral number, return. Otherwise, return plus. Assert. Base is finite
And this is in chatbot's code.
if abs are
Oh, I'll go over to the Mac.
base equals 1, return nan. See if abs are base.
This is from the internet. I copied it. As chatbot said,
If abs are base 1,
shift right AX,
base equals 1, return nan.
shift right AXDL.
Assert
I'm gonna ask chatbot what this instruction does.
2. If base minus 0.
See if it notices if it's invalid or not. How did it build earlier?
Power, the result of base exponent when base is 1 or minus 1 and exponent is plus or when base note is 1 and exponent is nan, differs from IEE 754-2019. The first edition of ECMA script specified a result of nan for this operation, whereas later revisions of IEE 754 specified 1. The historical ECMA script behavior is preserved for compatibility reasons. 2. ECMA International 2024 6 1 6 1 for number, multiply, x, y. The abstract operation number, multiply takes arguments x, a number, and y, a number, and returns a number. It
Okay, it says summary. Logically, it shifts specified number of bits, specified DL, filling in zeros from the left.
IFX
Is it a valid instruction though?
return none is either plus or. Then, if y is either plus 0 or minus 0, return none. If y plus 0, return x. Return x is either plus or. Then, if x is either plus 0 or minus 0, return none. If x,
Chatbot's thinking.
y, return y is minus 0, then, if y is minus 0 or y minus 0, return plus 0. Else, return -0 is -0, then if x -0, return +0. Else, return -0. B, return r, x, r, y. Note finite precision multiplication is commutative, but not always associative. 6, 1, 6, 1, 5 number. Divide x, y. The abstract operation number.
Chatbot gave me broken assembly.
(2019) binary double precision arithmetic, producing the quotient of x and y where x is the dividend and y is the divisor. It performs the following steps when called: ifx, ifxa, b, c, ifa, ifa, a, ifxa, b, c, ifa, ifa is nan or y is nan. Return nan is either plus or. Then, if y is either plus or, return nan.
Chatbot said, then that was my mistake.
+0.
Plain and simple, that instruction is invalid and should have never been in the output.
Otherwise, return -0 is. Then, if x is +0 or x +0, return -0. Otherwise, return +0 is either +0 or -0. Then, if y is either plus.
So, I have more questions than answers, but I'm done for today. I'm gonna go to bed. I'll get answers later. It's frustrating. So, I'm gonna let the stream run on for 10 more minutes. And next stream I guess. But I'll let the stream run on 10 more minutes because that was all I sent. So if I let it run on 10 more minutes, I might send the whole thing. I hate everything. Alright. Peace.
Operands where n is the dividend and d is the divisor. It performs the following steps when called: if n is nan or d is nan, return nan. If n is either plus or, return nan. If d is either plus or, return n. If d is either +0 or -0, return nan. If n is either +0 or -0, return n. Assert n and d are finite and non-zero. Let quotient be r, n, r, d. Let q be truncate. Quotient. Let r be r, n, r, d, q. 0. If r equals 0 and n -0, return -0. 1. Return r. Note 2. The result of a floating point remainder operation as computed by the percent operator is not the same as the remainder operation defined by IEEE 754-2019. The IEEE 754-2019 remainder operation computes the remainder from a rounding division, not a truncating division, and so its behavior is not analogous to that of the usual integer remainder operator. Instead, the ECMA script language defines percent on floating point operations to behave in a manner analogous to that of the Java integer remainder operator. This may be compared with the C library function fmod, 1, 6, 1, 7 number, add, x, y. The abstract operation number, add takes arguments x, a number, and y, a number, and returns a number. It performs addition according to the rules of IEEE 754-2019, binary double precision arithmetic, producing the sum of its arguments. It performs the following steps when called: if x is nan or y is nan, return nan. If x is plus and y is, return nan. If x is and y is plus, return nan. If x is either plus or, return x. If y is either plus or, return y. Assert x and y are both finite. If x is -0 and y is -0, return -0. Return r, x plus r, y. Note finite precision addition is commutative, but not always associative. 6, 1, 6, 1, 8 number. Subtract x, y. The abstract operation number. Subtract takes arguments x, a number, and y, a number, and returns a number. It performs subtraction, producing the difference of its operands. X is the minuend and y is the subtrahend. It performs the following steps when called. Return number, add, x, number, an array minus, y, 34. ECMA International 2024. Note 1 in C and C++. The remainder operator accepts only integral operands. In ECMA script, it also accepts floating point operands. Note, it is always the case that x, y produces the same result as x plus y. 6, 1, 6, 1, 9 number, left shift, x, y, the abstract operation number. Left shift takes arguments x, a number, and y, a number, and returns an integral number. It performs the following steps when called. Little numby, to int 32, x, letter numby, to int 32, y, let shift count br, renum, modulo 32, return the result of left shifting num by shift count bits. The mathematical value of the result is exactly representable as a 32-bit 2's compleme NT-bit string, 1, 6, 1, 1, 0 number, signed right shift, x, y, the abstract operation number, signed right shift takes arguments x, a number, and y, a number, and returns an integral number. It performs the following steps when called. Little numby, to int 32, x, let renumb, to int 32, y, let shift count br, renum, modulo 32, return the result of performing a sign extending right shift of num by shift count bits. The most significant bit is propagated. The mathematical value of the result is exactly representable as a 32-bit 2's complement bit string, 1, 6, 1, 1, 1 number, and signed right shift, x, y, the abstract operation number, and signed right shift takes arguments x, a number, and y, a number, and returns an integral number. It performs the following steps when called. Little numby, to int 32, x, let renumb, to int 32, y, let shift count br, renum, modulo 32, return the result of performing a zero filling right shift of num by shift count bits. Vacated bits are filled with 0. The mathematical value of the result is exactly representable as a 32-bit unsigned bit string, 1, 6, 1, 1, 2 number, less than, x, y, the abstract operation number, less than takes arguments x, a number, and y, a number, and returns a boolean or undefined. It performs the following steps when called. If x is nan, return undefined. If y is nan, return undefined. If x is y, return false. If x is plus 0 and y is minus 0, return false. If x is minus 0 and y is plus 0, return false. If x is plus, return false. If y is plus, return true. If y is, return false. If x is, return true. 0. Assert, x and y are finite. 1. If r, x, r, y, return true. Otherwise, return false, 1, 6, 1, 1, 3 number, equal, x, y, the abstract operation number, equal takes arguments x, a number, and y, a number, and returns a boolean. It performs the following steps when called. If x is nan, return false. If y is nan, return false. ECMA International 2024 35. 3. If x is y, return true. If x is plus 0 and y is minus 0, return true. If x is minus 0 and y is plus 0, return true. Return false, 1, 6, 1, 1, 4 number, same value, x, y, the abstract operation number, same value takes arguments x, a number, and y, a number, and returns a boolean. It performs the following steps when called. If x is nan and y is nan, return true. If x is plus 0 and y is minus 0, return false. If x is minus 0 and y is plus 0, return false. If x is y, return true. Return false, 1, 6, 1, 1, 5 number, same value 0, x, y, the abstract operation number, same value 0 takes arguments x, a number, and y, a number, and returns a boolean. It performs the following steps when called. If x is nan and y is nan, return true. If x is plus 0 and y is minus 0, return true. If x is minus 0 and y is plus 0, return true. If x is y, return true. Return false, 1, 6, 1, 1 6 number bitwise op, x, y. The abstract operation number bitwise op takes argument ts op, and, or, x, a number, and y, a number, and returns an integral number. It performs the following steps when called. Little numby, to int 32, x, letter numby, to int 32, y, little bits be the 32-bit 2's complement bit string representing r, num. Let bits be the 32-bit 2's complement bit string representing r, num. If op is and, then a let result be the result of applying the bitwise and operation till bits and bits. Else if op is, then a let result be the result of applying the bitwise exclusive or XOR operation till bits and bits. Else assert op is be let result be the result of applying the bitwise inclusive or operation till bits and bits. Return the number value for the integer represented by the 32-bit 2's complement bit string result, 1, 6, 1, 1 7 number, bitwise and x, y. The abstract operation number, bitwise and takes arguments x, a number, and y, a number, and returns an integral number. It performs the following steps when called. 1. Return number bitwise op, and x, y, 1, 6, 1, 1 8 number, bitwise or x, y. The abstract operation number, bitwise or takes arguments x, a number, and y, a number, and returns an integral number. It performs the following steps when called. 1. Return number bitwise op, x, y, 6, ECMA International 2024, 6, 1, 6, 1, 1 9 number, bitwise or x, y. The abstract operation number, bitwise or takes arguments x, a number, and y, a number, and returns an integral number. It performs the following steps when called. 1. Return number bitwise op, x, y, 1, 6, 1, 2 0 number, to string, x, radix. The abstract operation number, to string takes arguments x, a number, and radix, an integer in the inclusive interval from 2 to 36, and returns a string. It represents x as a string using a positional numeral system with radix. The digits used in the representation of a number using radix are taken from the first R code units of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is in order. The representation of numbers with magnitude greater than or equal to 1 never includes leading zeros. It performs the following steps when called. If x is nan, return nan. If x is either plus 0 or minus 0, return 0. If x, minus 0, return the string concatenation of a number, to string, x, radix. If x is plus, return infinity. Let n, k, and s be integers such that k1, radix 1s, radix, s radix, k, is x, and k is as small as possible. Note that k is the number of digits in the representation of s using radix, that s is not divisible by radix, and that the least significant digit of s is not necessarily uniquely determined by these criteria. If radix 10 or n is in the inclusive interval from -5 to 21, then if nk, then I return the string concatenation of the code units of the k digits of the representation of s using radix, n, k occurrences of the code unit 0 times 0030, digit 0, b else if n, 0, then I return the string concatenation of the code units of the most significant n digits of the representation of s using radix. The code unit 0 times 002 e, full stop. The code units of the remaining k, n digits of the representation of s using radix. See else. I assert, n02. Return the string concatenation of the code unit 0 times 0030, digit 0. The code unit 0 times 002 e, full stop. N occurrences of the code unit 0 times 0030, Digit 0. The code units of the k digits of the representation of us using radix. Note: in this case, the input will be represented using scientific E notation, such as 1.2e plus 3. Assert: radix is 10. If n 0, then let exponent sign be the code unit 0 times 002d hyphen minus 0. Else, let exponent sign be the code unit 0 times 002b plus sign 11. If k equals 1,